Yeah, I'm not sure how this is gonna go, but we'll see. I feel like I'm relatively confident in the fundamentals of math and game dev, but I'm guessing I'm gonna get questions and I'm gonna not be able to answer them. I'm not as confident in math as I am in like general game dev, but we'll see how it goes. I think it'll be useful. I'm probably gonna go through very fundamental stuff, so if you're already good at math, then this is probably gonna be too basic for you. But you're very welcome to join, regardless. So yeah. Also, we have a Thor in the background. I guess I really like math from like a very like philosophical perspective, I suppose. Aside from all the practicalities, like it's really practical to know math. I think there's something very beautiful about like this system that is incredibly fundamental to the way we observe and analyze the world. Like, it's kind of the very fundamentals of how we observe time, how we observe space, how we observe quantity, how we observe change, like all of that stuff. It's so extremely fundamental that I think math is something that like exists absolutely everywhere across the universe, like regardless of species. Like it's kind of this discovered abstract world, which I think is really fascinating. So yeah, like other societies in on other planets would probably also have something that's very similar to the way we do math, right? Because that's just the that's just the fundamentals of quantity and stuff, right? It would take an entirely different universe for math not to exist in the form that it does here, right? It's really cool. So I think it's interesting that like if you make a discovery within the universe of mathematics, that's a kind of universal discovery. Like a circle constant, for instance, is something that other societies probably also have discovered, right? Um, Although hopefully they would be more intelligent and use tau instead of pi, but oh well. Which I think that's super cool. And then of course they would use like different symbols and whatnot to represent numbers, but the underlying ideas are still universal, which I think is super cool. Thor, hi. Meow. The language of the universe, maybe. I'm not sure what the language of the universe would be. I feel like that's more physics, but will there be quaternions today? There might be, but I'm gonna approach this from a pretty pragmatic perspective. So I'm not gonna go into detail on how, quaternions work internally. I'm gonna talk about how to use quaternions in Unity for rotations. So I'm gonna try to approach it from a like practical, this is how you use it in situations like this, rather than, this is how matrices work in explicit detail, or this is how quaternions work in explicit detail, because that's generally not relevant for game development, right? Even though it might be interesting, I think it's outside of the scope of this stream. Is there any specific concept you would like me to cover that like might be relevant to game dev? I have a list of things that I want to talk about, but I might not have like good specific examples of stuff. Quaternions, proper mirrors, basic vectors, matrices. I think we can do polar coordinates, sure. Math in the context of shaders, proper mirrors. Are we gonna go to the math library? Probably, yeah, we're gonna use that one. I think a lot of this is going to be mostly theory, like not like entirely everything inside of Unity, but I think we can use Unity to visualize this stuff, right? So actually I should start Unity. So like I mentioned before, I'm gonna try to keep this a pretty like pragmatic tutorial. So I'm not gonna go into like how quaternions work in terms of like the guts of a quaternion and imaginary numbers and all of that stuff, because it's not really like relevant in order to use quaternions in Unity. Same thing with like rotation in X-dimensional space. It's one of those things that's like mathematically it might be interesting, but I think for game dev it's not very applicable unless you're making a 4-dimensional or 5-dimensional game or something. But yeah, I don't think that's such a specialized case. Math in the context of shaders. We could talk a bit about shaders. It is very, very relevant within shaders. So yeah, maybe. We did do the one shader tutorial though. I did talk a little bit about math in that one, like using generating waves across some given space and so forth, but yeah. Think we can figure out the surface area of your cat. I mean, if you include individual hairs, that's going to be a very large surface area. Have you ever done stuff in Unreal? Yes, I have. Can we use customized part for Unity physics? What do you mean? Isn't basically every 3D game 4D space? Not really. I mean, depending on how you define space in that case, right? Like if you do, oh, the 3 first dimensions are geometrical, and then the 4th one is time, then sure, it's 4-dimensional if those are the dimensions you want to use. But it's more a question of like, what is the dimension in this case, right? So I think in this case, I'm probably going to talk about dimensions only in terms of geometric dimensions, and not spatial ones. Or wait, geometric ones and not temporal ones. There we go. Math in 3D is a movement and or other stuff. It could be anything, like comparing points, for instance, like how far away is this object from this object? And then immediately now we have a math problem, right? You know, how close are these 2 objects? That's the thing we need to be able to solve, right? Yeah, so it's questions like that, or, you know, is this one looking toward this other object? How do we do that math? Like these types of things pop up a lot, and a lot of this is just vector math. So one of the core things we're going to talk about is vector math, and then also we're going to do trigonometry. And let's see, hold on, I just need to start a project. What do we call this? Math tutorial? Sounds a bit generic, but it's fine. Can we rewrite some functions interaction for physics interaction in Unity? Interaction of objects, for example? Generally not. It's pretty limited in the way that you can't really like just get collision stuff from the you can't really just get the collision stuff from the physics engine without having the physics engine also act on those objects. So if you want to do like a custom collision, then you kind of need to write the whole thing yourself, I'm pretty sure. Like you can do like triggers that intersect with stuff and you get like detect that, but you don't get the specific impact point, you don't get the relative velocity and all of that stuff that you need, right? So it's not always like fully useful for that, right? Yeah. Dot cross product, yeah, this will be covered, especially dot product. Cross product is a bit more rare because it's not that often used, but it might as well cover it. It's useful. Yeah. I thought maybe if we also have time, I could also talk about derivatives, but that might be a bit too advanced. But there are ways of framing derivatives that make a lot more sense, I think, than how some people tend to try to explain them. Her cat's interested in math for game dev? I'm not sure. I think Thor just wants to play right now. Because Thor has been not playing throughout all of the night. But anyway. That's my first think of the distance from 2 objects. Yeah, that would give you the displacement, not the distance. So the displacement is the vector from one point to the final point, right? But in order to get the distance, you need the length of that vector, right? Yeah. So Tommy says that that's a direction from point A to point B. Note that that direction is not normalized though. So generally when you say direction, you usually mean a normalized vector because it has a length of 1. We're going to talk about normalized vectors as well. So using delta time to do frame rate independent movements. Yeah, that's something that's pretty useful. Heck, I wonder if we should talk about that when we talk about derivatives. Unity shader language is HLSL, right? Yeah, pretty much. It's like CG, but also HLSL. It's weird. It's a weird combination of them, so... Okay, I'm gonna head to the bathroom. gets converted to GLSL. It gets converted to whatever the target platform requires it to get converted to. Because Unity does a lot of like cross-compilation between different languages, so that it works on whatever platform you're targeting, right? Wait, hi Thor. Hi. I'm targeting web or Android, yeah. Yeah, in that case it would be GLSL, yeah. Does Unity use Spirit under the hood? I don't remember. I recognize Spirit, but I forgot what it is. I don't know. But I'll be right back. Need to go to the bathroom. Because I didn't do that before streaming. God damn it. But that's why we have the pre-stream. It's supposed to be shitty, and I'm supposed to not pay attention to things. So... He does not appreciate this either. Oh. Cat or it didn't happen. Well, here's the cat. Don't forget to tweet. Heck. Do I tweet? I don't know. Okay, so here's a question. What a lot of people say, like, I hate math, or like math is so hard, or math is so difficult to get a grasp of. What is it about math that you think is the most confusing part, or the something that you think hasn't really been properly explained to you? Because there are a lot of people I've noticed who just really dislike math, and I'm not entirely sure why, and I hope I might be able to mitigate that. Fermat theorem proof, I'm not gonna do that. That seems very difficult. That is way beyond me. Bezier curves are confusing. Are you trying to bait me into explaining Bezier curves again? God damn it. Thank you for the follow. I've been bad at keeping up with thanking people for following, because during these tutorials I've been trying to keep focused, but also there's been so many people who are coming to these streams, so yeah, sorry for like not having been able to keep up with everything. Have I missed anything yet? No, not really, just a pre-stream. We've just been talking. I think a lot of people just had some bad time in school because of bad math teachers. Yeah, and then the factor of just being young, because it's like, being young, you tend to have so many things you think about, and it's hard to focus on things you're not super interested in, right? Yeah. Thor. Biggest problem I think people have with maths in school is there are holes in their knowledge and false mindset when starting to learn it. It's pretty entertaining seeing you ramble about Bezier curves a lot. I mean, inevitably, if I talk about math, I'm going to talk about Bezier curves. I need to try to not do that, I think. Thank you, Mikachu. That's super nice of you. I've noticed even teachers refer to math as hard rather than explaining that it can be fun, so I think it's passed on a bit. Gotcha. You know, okay, so all right. Anything... what was the, when all of you did math, do you remember a specific topic where you were like, even though you might know it now, like, what was the topic in math that you found the most confusing? Or something that took a long time to, like, grasp within math? Like, I remember something that I had a problem with in the beginning was derivatives. I think, my teacher did not explain that in a good way. So I remember derivatives being like incredibly difficult to understand. Yeah, like derivatives as well as integrations. Yeah, there was something about the way that they explained it, but anyway. Tensors can be pretty hard. I don't even know what tensors are. Oh, so like, okay, gotcha. So they're like basis vectors in a given space? Okay, neat. Um, Shall I launch Unity and follow along? If you want to. I'm probably going to structure this tutorial as not waiting for people to catch up, because there's going to be a lot of theory. I'm mostly going to be demonstrating stuff, but this is going to be on YouTube, so whoever wants to, like, watch it again, then you can do that if you want to follow along. But I'm going to not, like, wait for people, so... but yeah, totally follow along if you want to. That's totally fine. One thing that it took me way too long to realize is how to break down matrix multiplication in a graphical way, if that makes sense. Gotcha, yeah. Integration, differentiation. I couldn't see the point until my first job doing processing seismic surveys, and it was all integration, yeah. Have you ever thought about creating an engine from scratch? I've thought about it, but it seems like it's too much work for me to make a game, so that it's just not worth it for me. I generally get bored too quickly unless I get results. So for me, if my goal is I want to make a game, then I'm going to use an engine because it's so much more efficient. It's going to take too long to write my own engine. But I might do it, but then it's only because I want to learn the guts of an engine, right? Not in order to make a game. So yeah, I've thought about it, but it's like... I almost immediately discard it because it's not like viable for, you know, any of the projects that I want to make so far. Yeah, so I tend to focus a bit more on high level stuff. It's more like engines and even programming and all of that stuff is kind of like means to an end, sort of. It's the thing you have to do to, you know, make a game, right? Yeah. Have a math YouTube playlist. You want me to share that on your Discord? Feel free to share it if you want to. Yeah, go for it. We don't really have a good channel for sharing YouTube stuff. I guess the closest channel would be Dev, I think. Alright, so, heck, I feel like this might be a bit too basic for many of you, because I think a lot of you like already know math to a great extent. So I'm sorry if it's going to be a bit too basic. Like, for instance, I'm not going to go through matrix multiplication, because that's just too... you don't need to know that to make games, right? And the same thing with like 3 Blue 1 Brown. It's a really good YouTube channel, and they go really in depth on a lot of like really cool math concepts, but it's not really needed for games. Like the math you need for games is like generally pretty basic. But yeah, even though it's pretty basic to me now, it is quite a lot of stuff. And if you don't like have a good grasp of them, then, you know, a lot of problems are going to be tricky to solve. You know, there's so much vector math in game dev. So yeah, for general math, yeah, sure. Yeah, it's a good channel. All right, are we ready to get started? Is there anything else you want to let me know before we get started? Actually, you can ask questions during the whole thing. It's not like super formal, but... Okay, music is coming through, I think, right? Can you confirm before we get started? Music's fine. Cool. I hear music. Music is good. Music is good. I appreciate music in general. Alright, let's do this. This might not be the smoothest tutorial, because again, these are improvised, so I haven't like set up a good course or something like that. I might like condense, I might actually make a proper YouTube video on the basics of math. So I guess this would be kind of like a test to see Is there enough to talk about? Is there too much to talk about? How can we balance the amount of content you need to learn, you know, for essential game dev math? I've always sort of been of the opinion that the amount of math you need to know for game development is actually not that much. Like, you don't even need to know integrations. You don't need to know differential equations. You don't need to know, you know, how matrices work internally. You don't need to know how quaternions work internally, because if you're making something in an engine, you don't need to do that type of stuff. So, yeah, so in game development nowadays, in Unity and Unreal, the type of math you need to know is kind of basic algebra. You need to do a lot of vector math. Vector math is probably the most important one. It's really good to know some physics and the basics of derivatives, like what does it mean to have a rate of change, right? So that's super important. And trigonometry can be super useful. Not always, but it can be. But then there's a lot of like one-dimensional manipulation, you know, remapping a range, scaling something, offsetting something, blending between two states, that type of stuff. That's very, very common. And then, of course, the idea of having local space and world space is very, very common in game engines too. So yeah, so we're going to talk about that. I think that's sort of the vague plan I have. I have written a bunch of notes on things we could talk about. But yeah, always feel free to let me know if there's anything you want me to cover. If I was like unclear about whatever, then feel free to let me know. Yeah, all right, does that make sense? Are we ready to go? I think we are, right? Let's go to the desktop view. There we go. All right, I think we're going to start with a neat little algebra exercise, because this is a very, very typical thing you might see in a game engine, right? So let's do this. Also, this color is different from this color, so I'm just going to fix that right now because that bothers me. It was like off by a tiny amount. There we go. Sorry. What layer is this? Good. All right. So let's go to a very simple example where you might be setting up a game. You're setting up some sort of game that has units with health bars, and then these health bars, you want them to, you know, have a texture inside of them, or like a sprite for the health bar graphic itself, and then you want a bar, and then you want to be able to change that one based on how much health your character has, right? And your character might have health values between, you know, 0 and something, right? So say you do have this health bar. Let's see how big we should make this. That's a great health bar. What a symmetrical and uniform health bar. Okay, so say you do have a health bar, and you want to fill this to some value somewhere, right? So let's say you got this value right here. So then you might run into some issues. So say you have your you have the width of this one. You have the pixel width of the health bar, right? So that would be this extent right here. So this is, let's see, what do we call this one? px width, for instance, of the full bar. What do we call that one? Container bar, maybe? Okay, so wait, that's not how you spell width. There we go. Bar. Okay, we got the pixel width of this bar right here, right? Okay, what else have we got? Well, we have a player somewhere in the world, right? And the player probably has some sort of health value, right? And the health value has some number. You have a maximum health and you have a current health, right? So let's say you have your health max, and that might be some number, right? And then you have your health current. I should get a tablet. This is not ideal. Is this readable, by the way? My handwriting or mouse writing is not the best. Okay, so we've got the width of the health bar, we got the current health, we got the maximum health, and what else have we got? So we might want to have a sprite in this one. So let's say we have a texture that we then want to stretch or something, right? So say we have a health bar sprite that's like a texture asset, right? And this sprite also has a width. So actually, let's use a different color for that one to clarify things. You're not using a tablet? No, I'm not. Okay, so we have these values. So far we have 3 values. We needed 1 more, right? So say we want this graphic to map a sprite onto this one, right? You have your sprite right here, and the sprite itself has a width too. Let's call it SP. Hold on. SP lowercase s PR width. Okay, so there we go. So this is again a pixel width. So actually we should probably do a there we go. Also this one shouldn't melt into the thing. There we go. Pixel sprite width. There we go. Cool. So now the question is, if we want to map this sprite and we want to put that one right here, what scale does this one need to have in order to fill the amount of health you have? So you have the pixel sprite width here, but that width of course doesn't match the full health bar. And then the question is, what do we scale this one by in order to fill this health bar so that the sprite is stretching all of this like cyan area, right? So how do we do that? This is kind of a typical example of like you have a lot of variables and then you need to remap a bunch of ranges, right? So there are a few steps that you can go through here that are pretty important to kind of know how they work and whatnot, right? So first off, what you probably want to know is the current amount of health relative to your full health, right? So you have your current health and you have your max health. So how do you get the percentage of health that you have given these two values? Well, if you want to get that, then there's a very simple way that where you can take the maximum the total, and then you have the current value, and that's kind of the fraction of the total, right? So if you do the current, there we go, divided by total, then you get a percentage for how much this one covers of the total. So this is just a simple division. We divide the current health by the maximum health, and then we get a percentage of how much health we have, right? So say the full range here is 100%, and then you have 50% here, so 25, so it's like somewhere here, right? Okay, so let's say this is 40% or something, right? So if this is 40%, then this one is going to give you 0.4, because that's how you usually write percentages, in case they are just like multipliers or something. And this is equivalent to 48%, right? Okay, so now we have a way to get the percentage of health, right? So we can call that PCT health. I need a smaller brush. PCT health. Cool. Okay, so now we have a way to get the percentage of health. So now how do we get how much it covers of the health bar? Well, the percentage of your health related to your health maximum is going to be the same as the percentage the bar should cover of the width of the health bar, right? So what we want is the pixel width of this bar right here. So how do we get that? Well, if we move things around a bit, which I should have done earlier to fit the percentage health in, then what we can do is that we can take the percentage of health and then multiply it by the pixel width of the bar. then we're going to get a percentage, we're going to get that same pixel value, but as a percentage of the full width of this bar, right? So if you do that, then you're going to end up with however wide this one is going to be. So the width of this one is the, let's see, px with bar. There we go. And then we, I cannot type, I'm sorry. Then multiply that by the percentage of health, right? So that's the PCT health. There we go. Okay, so that gives us a pixel width of how much the health bar should cover inside of the container of the health bar, right? Did that make sense, by the way? I hope that made sense. So we kind of get that percentage in pixels if we multiply a percentage by the full range, right? Okay, so now we're almost there, right? So, sorry we still a question, I'm not a game developer. Why not we just draw a region using sprites? I mean, you could draw the region too. Generally, you don't scale sprites, but for the intensive, for this purpose, we're just doing it for a math exercise. But yeah, it's pretty common though to have an object that has a specific size and then you scale it for the health bar. So that case is not like super rare. That can definitely happen. Like somebody mentioned in chat that they've already done it like a few days ago. Okay. So now we have kind of an interesting problem of this sprite right here has a specific width, and that width probably doesn't match the pixels, right? So let's say the width of this one is let's say the width is 4, for instance. So okay, so it has a width of 4 pixels wide, but then. So how do you make sure that the 4 pixel wide one can scale to fit this range right here? Thor, take it easy. Heckin' cat. Alright. So in order to do that, we need to convert between a few things. So you can think of this width number, this 4 right here, as you can reframe the way you state this one, right? So now currently this one is in pixels per sprite width, right? So it's pixels per sprite, if that makes sense. It's kind of, this is kind of the unit of this number. It's 4 pixels per sprite, and that's a value we can use in our calculation of this, right? But there's an interesting property that where you can do 1 divided by some value, and that will also flip the units. So if you have something like if you have 4 meters per second, for instance, if you do 1 divided by 4, so if you do 1 divided by 4, as in you just take 1 divided by the number you have, and then what happens is that you also flip the unit. So in that case, you get 4 meters per second is then the same thing as 0.25 seconds per meter. So you can see that we flipped it from meters per second to seconds per meter. And the way we flipped it was just do the reciprocal of it, which is just 1 divided by the value, right? And if you take 1 divided by this, you flip it back to that value, right? So if something is moving at the speed of 4 meters per second, then flipping that can tell you how long does it take for this to traverse 1 meter, right? That's kind of seconds per meter. And what's that math operation called? It's the reciprocal. So that's a very useful tool to have, because this is something that you can do quite a lot, where you just flip a unit. So in this one, you can also do the same. So right now it's pixels per sprite, right? But we have a pixel value here. This is in pixel units. And if we want to know how many sprites we want to do per pixel, then we need to flip this one. So if we do that, then again, let's say it's 4. If we do 1 divided by 4, we then get a value 0.25, and the 0.25 would not be pixels per sprite, that would be sprites per pixel. So now we have this in a per pixel format. Now we know how many times we should have this sprite within a single pixel, right? So now that we have this unit, if we then take, actually we should name this one to something. So this should be like pixels per sprite or something, right? So px per sprite. There we go. Is that value. So the one thing we need to do now is to multiply this one by pixels per sprite, and then we get the scale of this object right here. So hold on. Need some more space. Okay, so say we had this one. The sprite is right here, and then we need to scale it with something. So that scale is then going to be this value we had right here. Just going to cut it out because I don't want to mess up my stuff. There we go. And then we take that one, and then we just multiply it by the pixels per sprite. So multiply it by pixels per sprite. So this is then going to give us the scale of this one in order for this one to have the same size as this one in pixels, right? So yeah, so that's the way we would get that scale. All right. So this is the type of stuff you do quite a lot. There are also different ways of doing this. So instead of getting the reciprocal of the pixels per sprite, you could also divide this by the width of this sprite. But that operation is like a bit more difficult to explain why that works. But I think it makes a lot of sense to have these units, because then you can kind of see that you have the full width of the health bar in pixels. You multiply that by a percentage. So that means that you're going to get a percentage of this one, and that unit is still in pixels. And then if you multiply that by something that is pixels per sprite, then what you get out of it is the scale of that sprite. Yeah. So then if we have used the scale value, we'd be able to extend this one to the same width as the other one, right? Yeah. All right, did that make sense? Or was this a very esoteric and strange example? Any questions about this, by the way? Should probably use a lasso tool more for marquee selections instead of doing weird things with the box selection. Well, so hello, Gosmod. So far, so good. Super. Do you want me to do this in code as well, or do you want me to keep it like theoretical and purely mathematical? Because I could do code examples as well. By scale, do you mean we'll repeat the sprite? In this case, it's just scaling up the object. As in you have some object, and then you multiply it by 2, then the object would just be like bigger. In this case, it would just be scaling in 1 dimension, so then it would be twice as wide, right? And then how you repeat that texture or whatever, that would be like, that would be a different thing. That's kind of, you know, what does the shader look like and yada yada. So that's kind of a separate thing, so we're not going to go fully into that. Yeah, hi. Yeah. But yeah, do let me know if you want like code example or something. It might take a bit longer, but it might be useful to like clarify how things work. Have you had your water? No. I'm sorry, I haven't. And thank you for reminding me. So we calculated the scale factor. Yeah, exactly. All right. Is there anything I'm guessing there are no more questions on this particular example. We could do an example of this. It probably... let's see, I'm trying to figure out if we can do this in a fast way and a visual way. Probably not. We probably don't need an example for this unless you specifically want it. I could do it, but I think it's not necessary. Or actually, it would kind of clarify things a bit better. Let's do it. I'm down for doing this. Thank you for the follow, Goss Mods. How do we set this up? Actually, this wouldn't contain the sprite width, so it wouldn't be exactly the same. No, actually, let's skip it. Let's not do it. It's going to be a bit tricky to set up. If I had, like, I should have prepared some better tool for setting that up, but, yeah, okay. All right, let's see, what's next? We've covered that, so, yeah, so this type of example of, like, finding a scale value of something, or, you know, all of that type of stuff is, like, super common. So another, like, very useful tool that I use to figure out scale is kind of like to think of things as, you know, say I have my value A, and then I want to find a scale factor so that A can become some other value, right? I want A to become B when multiplying it by something, right? So in this case, we wanted the width of this one, or the width of the scale of the sprite should become the same as this width by multiplying by something. But I don't know what something that is, but I might know both A and B. Like, I know the source value, I know the target value. So then all I need to figure out is what I need to multiply by here. I need to figure out the x, right? So as soon as you have this equation right here, you can just use algebra to, like, reshuffle this. If you divide both sides by A, then what you're going to end up with is that you're going to move this, whoops, brush, there we go. So if you divide both sides by A, then it's kind of like you're moving the A to the other side, right? Because A divided by A is 1, and then you do 1 multiplied by x, and then you end up with this, right? So then you get B divided by a very flat A for some reason. Yeah, so that's a very useful useful way to think about things. So whenever you want to find a multiplier, you do, you know, I have my value multiplied by something equals a third target value, right? And then you just, like, reorder the structure like this. And then you can figure that out by just running the numbers for B divided by A. Or if it's dynamic, you would just get the number automatically, right? Yeah. But that's basic algebra, and I'm guessing most of you have sort of a grasp of that. Yeah. Okay, so I was considering talking about graphs of functions, but functions can be a bit confusing because functions look like they operate in 2D space, but they don't really, so it might be more confusing than useful. But we'll see. In case we need to talk about graphs, we'll do it, but I don't think that's necessary. So now we sort of talked about range transformation and scaling, which is something you do a lot. You know, we had the some range of health, the current health to the max health to a different range of a health bar with a specific width. So these are just, like, one-dimensional scales that we had to remap and do stuff with, right? Yeah, so that's what we've been doing now. All right, so offsetting. We didn't do any offsetting now, but might be useful to talk about that when we talk about vectors. That's more relevant there. There we go. Okay. Don't know when we're going to talk about this. Integers and arrays and indices and loops. This is one of those things that is very fundamental, but you probably don't really talk about it much, as in, like, how does it actually work? How do we use indices and whatnot? Should we talk about that as well, or do you think that's a bit too basic? I don't know what the current skill level of the chat is right now. Also, thank you for the follows. I'm very warm. I need to fix my hair. So you use iteration and erase so much in code. So if you don't have a grasp of the how the length of an array works, how you get indices from that one, how the indices relate to the number of elements and whatnot, I feel like you're gonna have a hard time. So this is super fundamental, but I think a lot of people already know it, so maybe I'll skip that. Okay, so let's go to vectors. That's probably the most important thing. If you're gonna learn one piece of math in game dev, it's vectors. Like, it's almost arguably more important than algebra within game dev. So let's talk about vectors. Hi, Thar. How are you doing? Meow. I think the cat may be asking for a close-up. He had one close-up and then he disagreed. I'm just gonna sit with this cat toy in my lap and hopefully he's satisfied with the prospect of me almost playing with him. Cat need math. Probably do some math. Some intuitive math in their brains when like jumping or chasing something. That's some proper derivatives. Well, there he goes. Okay, vectors. Let's talk about vectors. Vectors are super neat. Okay, so let's set up something like a let's set up a number line. You're probably familiar with a number line. You have a line that is pointing in some direction, and you have some values along this line. You have 0, you have 1, you have 2, that's not a 2, 3, 4, and so forth, right? Actually, let's add 5 for completeness. Well, it's not called completeness. What's the word for... Anyway. Okay, so just if you have regular values in math, right? So you have a value of 2. You can kind of think of the value 2 as a one-dimensional vector. So the value 2, if that's an arrow pointing from 0, this would be a one-dimensional vector with the length 2 and also the value 2. So this is a one-dimensional vector with 2. Okay, I cannot draw 2s right now for some reason. They become super wonky. All right. So if we then want to add 2 to something else, if we want to do 2 plus 3, for instance, then it's kind of like we're adding arrows together. So if we stack another arrow, say the value 3 would also be an arrow from 0 all the way to 3, right? So now we have 2 values and 2 arrows. And so these are 2 one-dimensional vectors. So if we add 2 and 3 together, you obviously get 5, as you already know. So if you get 5, then 5 is another vector that is pointing all the way from 0 again. The height of these doesn't matter, by the way. They all should be stacked at the bottom. But anyway, so you get another vector of length 5, right? But the reason I talk about one-dimensional vectors like this is I want you to think of addition as adding 2 things, adding 2 lengths together. So if you want to get to the value 5 from these 2, you can simply take this arrow and then tack it onto the front of the next arrow. So by doing that, you can kind of see that this one adds up to 5, right? So you take one vector or one value and then add another value on top of that, and then get another one in the end. But this is a combination of these 2, right? So that's kind of a one-dimensional look at vectors. But generally when you use vectors, you use them in 3D or 2D, right? So now let's expand this to 3D. So let's take these things, move them around a bit, and actually, let's make a new layer for those. All right, so now we looked at this in 1D, and now let's go 2D. So in 2D, you tend to have multiple axes. You have 2 axes. So this is the x-axis right now. And then we're going to have another axis that goes vertically. And these are always exactly perpendicular because it's a coordinate system. So you have your y-axis here, and then again you have numbers here. So you have 1, 2, 3, 4, and 5, right? Okay, so as you saw here, we had these one-dimensional vectors, and they have a value of 3, and then that's an arrow going from 0 to 3, or that's one way to visualize it, right? And when you visualize it like that, the addition makes a lot of sense, because you just, you know, take one end of the arrow, tack it onto another, and then you get the full arrow, right? So let's do this in 2D now. So 2D coordinates, instead of just being a single value, you have two values, and they're always in the order of x and y. So first we have the x coordinate. So let's make a vector that goes from, say, from here to here. Okay, so what values does this one have? Well, the x coordinate of this one is going to be this one right here. So 3 is our x value, and the y coordinate is going to be the value right here, and that's 2. All right, so 3 and 2, so that's the coordinate of the vector. So if we want to, you know, type this vector out just mathematically, usually you have it in like parentheses or like curly brackets or something. So in this case, the x coordinate would be 3, and the y coordinate, separated by comma usually, would be 2, right? This bracket didn't fit, damn it. 3 and 2. Okay, so now we have a vector, a two-dimensional vector, or a two-dimensional coordinate at 3, 2. And again, 3 is the x-axis, and the 2 is the y-axis. It's always in that order. So you got x and y. Can you get an accumulated vector length from a vector 2? What do you mean by accumulated? You can get a length of this one, absolutely. I'm not sure what to mean by accumulated. Okay, so now let's do addition again. So now we have this vector. Let's add another vector. We could go a bit funky. So let's say we go for something on the negative side. So if we go back here, we have -1 and we have -2, right? And then the y-axis goes negative down here, but we're not going to go there. So let's make another vector. Now this one, we're going to do an arrow. Let's see. Let's do an arrow here. This one is intersecting the 1. I'm sorry about that. Maybe I should color code this one, actually, now that I think about it. Just one length, assume x and y would be accumulated. Gotcha. We're going to talk about vector length too. We're going to get to that after addition and subtraction. All right, so now we have another vector. So this vector right here, again, we'll look at the x-coordinate first and then the y-coordinate. So the x-coordinate of this one is going to be -1, and the y-coordinate of this one is going to be the same. It's going to be 2. So parentheses should be preferred over curly brackets. Gotcha. All right, so, okay, so the coordinate of this one would be, let's see, right, we have -1 and 2, right? So we have, like, now I don't know if I should keep doing curly brackets or not. So -1 and 2. This is the coordinate of this vector right here. Okay, so how do we add these together then? Well, you basically do the exact same thing as you do here, but you do it per component. So what I mean by per component is per axis. So you add the x coordinates together, and then you add the y coordinates together, which then gives you a third vector. So again, we can use the same thing as we did here, where we take one arrow and we stack it on top of the other one. So if we do it with this one, we move this over here, then this vector is going to be added like this. So now this one is over here, and if we add these together, we're going to get a third vector that goes from here to here. So the purple one here is the sum of these two vectors. So in this case, thank you for the follow. Right, okay, so now we have a sum of these two because we just took this vector right here, added it on top of this vector, and then we ended up with this vector because we've not added them together. So what are the coordinates for this one? Well, for this one, we would have a, that would be x coordinate 2, right? Because we go all the way down there, and that has a value of 2. Sorry about the grid. So that one is at 2, and then y coordinate is 4. So 2, 4. So now we've added these two vectors together. And that's how vector addition works. And the kind of the simplified way of doing this would just be to do this per component. So if we look at the actual values of these two, we have 3 plus minus 1, which is 3 minus 1. So the x-coordinate of this one minus 1 is 2, right? And that's the x-coordinate. And then the y-coordinate, we take the y-coordinate 2 plus the y-coordinate of the other one, which is also 2. So that's 2 plus 2, and that makes 4. So that's the final vector we end up with. We just do the components of each, right? All right. I hope that made sense. And then you can also do subtraction. That is also something you can do. And subtraction is works in a very similar way, but you can sort of just invert one vector and then add them together. So if we want to do, actually I should mark this one as, let's see, we should call these A and B, and this is C. Okay, so C is in this case the same thing as A plus B, right? Okay, so if we want to do A minus B, we can think of it as just like flipping this one to the other side. So we reverse this vector by multiplying each number by -1. So in this case, the x-coordinate would become 1, the y-coordinate would become -2. And that vector points something like this, or well, I guess this is difficult to eyeball. So then this one would be the negated version of this vector right here. And you just negate each number. Then you get a vector pointing in the opposite direction. So if we do A minus B, we take B, flip it around, and then add them together. So that would give us this vector right here. And then we'd get a vector along the, the flat line right here, right? And this vector here, that would be A minus B. All right. So Unity has a bunch of built-in types. So if you're using Unity, then there's a type for vector 2s, there's a type for vector 3s. And if you just do one vector 2, you know, add one vector 2 plus another vector 2, Unity's going to do all of this for you. It's just going to add them together. You don't need to like manually do this per component. But this is kind of the basics of how you, like how you add vectors together. Did that make sense so far? Is there anything that was unclear? Also, sorry about the clutter. I should probably like plan what vectors to use to prevent overlap, but this is improvised, so, you know. So far, so good. All right. Okay. So we've done addition, subtraction, and we've done 2D coordinates. Okay, so you can sort of probably see that you can extend this to 3D, right? So all we do is we add one more component to each vector and one more axis to do things on, right? So we just add one more thing, and that would be the z-axis, right? Hold on. Wait, actually, is that correct? No, z-axis should be in the other direction. Anyway, negative z. Anyway. Okay, so this extends to 3D too, but it's easier to talk about 2D. All right. So, great. Somebody asked about distance. How do we get the length of a vector? So if you want to get the length of a vector, this is a bit cluttered now. I don't know if I should be using this one for that. There we go. Uncluttered version. There we go. It's beautiful. I'll have to redraw the one. Okay. So if you want to get the length of a vector, let's just do a maybe that one. So over here. So if you want to get the length of a vector, it's usually within Unity or any math libraries, that tends to be built in. There's almost always a way to get the length of the vector itself. I could go through the math behind it if you want to, but basically the so this vector right here has an x-coordinate of 5 and a y-coordinate of 3. So this is 5, 3. So then if you ask for the length of a vector, then, these two contain the length of the, the x-axis. The 5 represents the kind of total distance here, right? That one. So that's kind of the length or the extent along the x-axis. And then if you do the y-coordinate of 3, then that's kind of the length of this right here. So if you think of it as a triangle, the x-coordinate or the y-coordinate would be the length of this side of the triangle, right? And so forth. Okay. So then the length of this one is going to be longer than the x-axis, right? Because this one, if you imagine rotating this one down, it's going to be a bit longer than 5. So okay, so how do you get the distance of a vector? There's if you remember Pythagoras, there's I don't know how to pronounce it in English, like Pythagorean theorem or whatever, Pythagoras' thing. That one is the thing you can use to get the length of a vector. And it's kind of you can kind of just like memorize it, I suppose. So if you want to get specifically the Euclidean length of this one, I guess that's a bit too, I guess I shouldn't talk about different length norms, but anyway. So the way to do that, you take the x-coordinate, so the x-coordinates, and then you square that, and then you add that with the y-coordinate. So again, remember, this is the x-coordinate, x-coordinate, y-coordinate. So we take the x-coordinate, square that, as in multiply it by itself, and then you take the y-coordinates, square that, as in multiply it by itself, and then you take the square root of that. And if you do that, then if you take the square root of that, then that gives you the distance, or the Euclidean distance specifically. So this will give you the length of the vector. So this is length. There we go. Okay, so this one is extremely useful. It's not exactly checking distance between 2 points, but this can be used to do that. So right now we have, so right now this is just a straight up formula for getting the length of a vector. But remember that you can interpret these as points and not just vectors in and of themselves, right? So if you do have another one, let's say this vector right here, different color. Actually, I should probably do something that would yield an angle vector. There we go. Okay, so if we want to know the distance between these 2 points, so you have this point right here and this point right here, what we need to know is this distance right here, right? Or, well, a bit less skew. So we need to know this distance. So now we have, it's a bit of a different problem. We can't just straight up use this one, because if we do that, then, you know, what numbers do we plug into x and y? Because we have, you know, one x and y coordinate for this one, and another one for this, right? In this case, this one would be 1 and 4, right? Okay, so if you remember the subtraction we did over here, we can use subtraction to get a vector that has the same length as the distance between 2 points. So, so if you look at these right here, so we had vector A, this vector right here, and then we had vector B, this one right here. When we subtracted A from B, that's a shortcut in Photoshop I did not know about. What is happening? There we go. So now if we take A minus B, you can see that we got this vector, the purple one that's lying like along the floor. This vector is the same as a vector that would go between these 2 points. But vectors don't really have a location and an arrow, quote unquote. So this one is just like residing at 0. But the distance or the length of this one exactly lines up between these two. And the same thing happens down here. So if you take this point and this vector, where we take, let's call this A, god damn it, and then we'll have vector B, and then we take A minus B, and if we grab the purple color again, then imagine this vector, but negated, and again, that would be a -1 and -1 on the x-coordinate and -4 on the y-coordinate, right? Because we just negate both of these, and that arrow would point in the exact opposite relative to the origin, right? So now this arrow, if we add this to this one, we're going to end up with a point that goes down here somewhere. We're going to end up with -1 on the y-axis, so that's somewhere here. And the x-axis is going to be 4. Because again, we can do this component-wise. X would be 5 minus 1, which is 4, so that's this x-axis right there. And then the y-coordinates would be 4 minus 3, or no, sorry, 3 minus 4, and then that gives us -1, right? So now we have a vector down here. So you can also imagine that as an arrow pointing like this, right? And if you look at this, this vector is the same length as this distance right here. So if we want to get the distance between 2 points, we simply subtract one from the other and then do the length of that vector. So if you want to get the distance, given 2 vectors, you can just first subtract one from the other and then do the length formula, and then everything's going to work. So that's kind of a quick way to, if you don't have a specific distance function, but you do have a length function, then you can do that, where you just subtract one from the other, do the length function, and then you got it, right? Okay. Did that make sense, by the way? I guess I could write the formula for that too, if you want. Also, thank you for the follows. But it would be very similar to this one. It's basically the same thing, but the what is happening with my brush? I want a normal brush. Hey, Photoshop. So basically, you take a dot x. So dot is usually the way we indicate that we want to get a specific field inside of that one. So a dot x would be the x coordinate of a, right? So we do a dot x, and then we subtract b dot x. Now we're kind of like doing this manually. B dot x. And then I need a neutral color. I've just got color colors, but no neutral colors. There we go. Okay. There we go. A minus B, that's a bit too dark. Makes me sad. Make a less sad color. Yeah. There we go. That's better. A minus B, and then we square that one again, same thing as last time. And then we add that with another one where we do A dot Y subtracted by B dot Y, also squared. And then finally we do the square root of all of this. So this is in case you wanted to do like a full, yeah, to do the whole thing basically, where you take a distance between 2 points, right? But usually you don't have to memorize this. Like you really don't have to. If you want to get the distance between 2 points in Unity, you would do vector3 dot distance and then pass the 2 vectors in, right? Yeah, but it might be useful and helpful to know the math behind it. I don't know. And one thing to note here is that the order in which you subtract doesn't matter. So in this case, we did A minus B, right? Where we took the negated version of B and added that here. But we might as well do the other way around. If we take the negated version of A, which is pointing in this direction, and then add that onto B, we're going to get something like this vector right here. And then you can see that that vector has the same length as this one. So it really doesn't matter which one we subtract first, because this has the same length. It has a different direction though, which can be super important to know. Okay, so speaking of directions, there's something in when you talk about vectors that's very useful, and that is normalized vectors. So a normalized vector is a vector that has a length of exactly 1. So why is this useful? That it's something that you see absolutely everywhere in games and a lot in math too. So a normalized vector is a vector that has a length of 1, which means that the arrow, or the quote-unquote arrow that we draw, is always going to lie within a perfect circle. As you can see, I drew a perfect circle on this graph. So if you take a vector like this one and you quote-unquote normalize it, then you get this vector right here. It's the same direction, but it has a length of 1, right? Yeah. Hold on. Sorry, I had a cat toy in my lap. You usually remember that I'm subtracting from target to get vector and local coordinate to it. Right. Okay, so usually normalized vectors are used for directions. So quite often when you say direction, you quite often mean a normalized vector. So if you want to get the direction from, say, B to A, then generally this is not the vector you're looking for. You want this vector, but you want it normalized, right? So now this is a very short vector. It goes from here to here. So what is that vector? Well, it is the direction from B to A, because if you move this one, you can see that that vector is pointing directly towards A over here, right? So it's quite often where you have 2 objects in a game, you want to know what's the direction to some, you want to get the direction to some other point. So how do you do that? Well, you can already see that by subtracting A minus B, which is the vector we have here, A minus B. If you do A minus B, you get this vector, and just normalizing that one gives you the direction. So to get the direction from one point to another, all you need to do is to do the target minus the source. That's how you get a direction from some source to some target, right? So in this case, we imagine B being the source, A being the target, and then A minus B will then be kind of the displacement between those two. But we also need to normalize that one, right? Because we want it to be a real direction and not just the displacement between these two. We need to normalize it. So if you want to normalize a vector, usually there's a function called normalize, and you always use that one pretty much. If you want to do it manually, you basically divide it by its length, and that's how you normalize a vector. So if you want to do the normalized version of a minus b, you would divide by the length of that, which, hold on, this one is sad. I'm tilting my head because the thing was tilted. So if you want to get that, then you divide it by the length of a minus b. And which is a bit different in math. You wouldn't write length. In math, if you want the length of a vector, I think you would do 2 vertical lines. I'm not sure if that means normalized or length, but yeah. So you want the length of that one, and then taking the vector divided by the length, and then you get a normalized version of that vector, which means that it has a length of 1. So that's a way you can get a direction from B to A. So just to clarify, that's the direction. No. Did I just copy the whole? No, okay. Absolute. I don't remember if like... Oh, right. If you want to do normalized vector, use the hat thing. You have a vector, and then you do a hat, and that's a normalized vector, I think. Whereas this would be the magnitude or the length of the vector, right? Yeah. Okay, anyway, so this would be the direction from B to A. All right. Also, thank you so much for the Prime sub, Erg. Heck, awesome as always. Thank you. Hydrobot hasn't been by yet today. Yeah, I don't know what's happened to Hydrobot. Heck. Always had trouble figuring out how to easily track an object to another game object, like a player in a floating avatar. What do you mean by track an object to another game object? Did all of this make sense, by the way? This whole thing became a bit cluttered, but I hope it's legible to some extent. Yeah, I'm gonna drink some more water because I really need water. I don't have one. But I haven't been streaming for that long, so 1:30. So I'm probably gonna get one soon, so maybe I should take a pill or something. I should take it as soon as I notice it's starting, I think. So I usually get a headache when I do these educational streams. It actually happens when I teach in general, which is kind of annoying. And I thought it was because I didn't drink enough, but now, last stream I drank so much water, so... Any resources to follow up on essential math for game dev? There's probably people in chat who have good resources for that. For me, I don't really have any good resources, I think. But I've considered making a YouTube video that has a proper structured explanation of all of these things, instead of like improvising it as we're doing right now. Although the advantage of doing this is that you can ask questions, which is super useful. A minus b gives you x and y. How do you divide that by number? Right, we didn't actually talk about that. So, yeah, so if you have a vector like 1 and 4, if you multiply that by a number or divide it by a number, that happens per component. So if you have a, yeah, so if you have a vector that is 1, too thick, damn it. You have a vector 1 and 4, and then you divide that by 2, then you get another vector, but each component has been divided by 2. So in this case, that's going to be 0.5 and 2, right? Yeah, and it's the same thing for multiplication. So again, if you have a 1 and 4, and then you multiply that by 2, then you're going to get another vector that is 2 and 8, right? Okay, so good question, by the way. That's something that I should have done. All right, so let's see, what else? Right, so one advantage that's related to multiplying like this is that if you have a normalized vector, let's say you do have this one, the one that is pointing towards B, right? Like this is the normalized version of B. If you want to move along this vector at a specific distance, like say you do want to move along this one and you want to find a point that is exactly like, say, 2.5 units away or something, right? Then what you can do is you can multiply the normalized vector by 2.5, and what you're going to end up with is another vector that has the exact length 2.5. That's kind of the super useful property of normalized vectors, is that if you multiply them by a number, you're going to get a position, an offset from that has that exact distance, right? So this is extremely common to have a normalized vector multiplied by something, right? So say you're defining a radius of something like this, and you want to increase that radius by some number. Well, for every vector you have that's normalized inside of this circle, just multiplying it by, say, 3 would give you a circle that would envelop 3 instead, right? So this is an extremely useful thing to do, to have normalized vectors. Normalized vectors are, again, they're used absolutely everywhere, especially within shader coding. There are so many like normalized vectors over there for doing like lighting calculations and doing all of that type of stuff with, you know, surfaces. Yeah, so that's an incredibly useful thing to know about. Yeah. Do you have a schedule when you do lessons teaching, like a section by section list? Because I find that when you try to shoot from the hip and jump from topic to topic, you really do get worn out mentally. Whereas when you teach with a plan in mind, seems easy to present mentally. To some extent, it helps to plan. And I've sort of done that for this too, but I don't know. I don't think it makes that much of a difference, for me at least. Yeah. All right. We talked about this. We have not talked about dot product. Let's talk about the dot product. That is a very useful feature. Do I have axes that are not cluttered? I guess I don't. All right. The dot product is a super useful function that you can use with any vectors. So in most cases, when you use the dot product, you tend to use it with at least 1 or 2 normalized vectors, and that's usually the most common use case within games as well. So first I'm going to mention or talk about how the dot product works in terms of 2 normalized vectors. So the dot product function, you have dots, let's call it dot, and it has 2 parameters. You usually have 2 vectors. We can use A and B as usual, as we've done before. You have some vector A and you have some vector B. And then out from this, you get a single value. So instead of a vector, you get a value from this. So you have 2 vector inputs, vectors, and then the value you get out of this is just a single value. So what is this value and why is it useful? So here we go. Should probably do the value thing here just to point it out. All right, so let's draw one more coordinate system. Hope you're not going to get tired of coordinate systems. Something like that. Right, and then we have a distance of 1, so it's 0 here, and up here we have a distance of 1, And again, we have 1 here. So in the middle, we would have, 0.5. There we go. And here you would have 0.25 and so forth, right? So this is just between 0 and 1, as you can see. What's going on here? We're talking about math. Feel free to join in. Okay, so now we have a very simple coordinate system. It's between 0 and 1. And the coordinate system, of course, extends infinitely in each direction, but in this case, we're going to focus on this. Okay, so let's say we do have a vector, like, so let's say we have a vector that is pointing directly upwards, this one right here. Let's use that vector as a reference. So this is a vector that has the values, the x-coordinate is 0 because it's not, offset in this direction whatsoever. So this is a vector that is 0, and then on the y-axis it's 1, right? Like that. So this is a vector 0, 1. Okay. So then let's say we want to use this vector in our dot product operation. So now we have the vector A right here. Then we need another vector. So let's grab another vector. And let's say this next vector is also normalized. So what it means that it's normalized is that the length is exactly 1. So that means that any vectors that are normalized are going to lie within this region right here, right? Because this is kind of all of the distance is 1 to all of these points in this circle, right? If that makes sense. So if we want to have a normalized vector, it would have to point somewhere in this circle. So let's slap in another vector right here. Okay, so now we have 2 vectors. Oh, right, it's also called a unit circle. Okay, so now we have 2 vectors. We have vector A, and then we have vector B right here. So what's the dot product between these 2 vectors? Well, the dot product will give you, if you imagine this one tracing a line here, completely perpendicularly to that one, the dot product between A and B is this distance right here. This would be the results of the dot product. And again, remember the dot product gives you a value, not a vector. So it just gives you the distance of this one and not a vector. So with 2 normalized vectors, you get that distance right there. So what happens when you change B, for instance? So if you move B closer to A, like say B is over here, then the dot product would give you a length all the way up here, which is almost as long as the vector. So the value when the vectors are close to each other is going to be very close to 1, right? So this is going to be like 0.9 something, right? Okay, so you get like that value up there. But what if the vector is pointing here? Well, you can see that that one is somewhere here. So this would be like 0.7071 or something. And then you have, if that's the lower you go here, you can see the value is decreasing even further and so forth, right? So yeah, so if you keep doing that, you can see that this one is going even lower. And this one is, yeah, I don't know, this one would be like super low. Hold on, I'm going to reach out in a bit. So this would be 0.1 or whatever. Okay, so we keep doing this. So we keep rotating this vector. As we go further and further away from it, we're going to get negative values. So if it's perfectly perpendicular right here, we're going to get exactly 0. All right, so now if we continue moving along this line, or this circle, then this one is going to be like negative 95 or something. And then as soon as you go completely opposite, this one is going to be negative 1, or 0.95, sorry. Okay. And then if we go back here, we're going to get back to the same value. So it's like, it's horizontally symmetric in this case. So, you know, this vector right here would also be this value. Same thing with the vector going here. That would be the same thing as this value. Okay, so what you can think of when you have 2 normalized vectors where you do the dot product, a nice way to frame it is to consider it kind of like a value for how similarly they are pointing. If they point in the exact same direction, you get a value of 1. If they point in the perfectly perpendicular, you get a value of 0. if they are completely opposite, you get a value of -1. And this applies to any two normalized vectors. So you don't actually have to use, this vector, which happens to align with the up vector. You can do the dot product between this vector and this vector, and that would also give you that type of similarity value. So say you have another vector is pointing here, so then the dot product between this one and this one would be -1 because they're pointing in the exact opposite direction, if that makes sense. So any two normalized vectors has this behavior. And this is extremely useful. This is probably like 80% of the time that I use the dot product. This is why I use it, because I want a like similarity type of thing. Can you do a dot product with not normalized vectors? Will it have any meaning then? Yes, you can. There are different cases where you use the dot product. Another case is where you have one normalized vector and one non-normalized vector. So let's see. Should I do another coordinate system? All right, here's another coordinate system. 1, 1, 2, 2, 3, and so forth, right? These are getting small. They're a bit pixelated. I'm sorry. Okay, so if you want to do the dot product between one normalized vector, then say you have the one normalized vector is right here. So it's a let's make it blue because it's kind of unclear right now. So you have one vector here, and this one is normalized. And then you have another vector. Let's grab some purple. And then you have another vector that's not normalized. So you have this one. Something like this, right? Okay, so if you then do the dot product between these two, you can see that this one is not normalized. This one does not have a length of 1. This one is like 2 point something, right? That's the length of this vector. But this one is 1. So what happens when you do the dot product between these two is that you get the distance where this one is projected perpendicularly against the other vector, the normalized one. And then the distance you get is the distance right here. So it's very similar to this one, but in this case the distance can go beyond 1, right? So this distance right here in this case would be 2, right? Yeah, and again you can use vectors that point in like other directions. It doesn't matter what directions they're pointing, right? Okay. I hope that answered your question. Might be worth to mention that the dot product uses the cosine of the angle between normalized unit vectors. We haven't really gone to trigonometry yet, so I feel like that's not very relevant. That's why I'm not like talking about that. Which words in English do you use to make a difference between, example, vertical and up down? What do you mean? Up and down is vertical, or do you mean how to distinguish between vertical or horizontal, or I'm not sure. Anyway, so if you use a dot product between one normalized vector, one non-normalized vector, then you can think of it as a projection onto one infinite line, right? You project this point down into this one. So it's quite often the dot product can also be called a scalar projection. And this is why, because it's sort of projecting stuff. Yeah. So that's like one of the most common use cases for the dot product. Okay, so here's a practical example of where I've actually used this in game dev. So say you have a surface, right? You have floor of some sort. Then you have some object, and this object is hurling towards the surface. And this object is going to hit the surface and then bounce, right? Now I was working on setting up the sound for a bouncing sound. So then I had the problem of like, okay, if the object hits the surface like straight down like this, I want the sound to be pretty loud, right? So like this should be loud, But if the object is hitting it at a very like angle like this, a very like slight angle, then this one, I want this one to be much more silent. Or this one, what do you call it? Discrete? Silent? Less loud. Right. So then the question was like, okay, how do I muffled, sort of, quiet. Quiet is good. But quiet can be interpreted as like completely silent. But let's call it quiet. It's close. Okay, there we go. So how do I solve this? Well, you can see that we have some vectors here too, right? And again, this should work for any surface. It doesn't really matter the angle. So if the surface has this angle right here, then this one shouldn't be quiet. Then this vector should be loud, because now this one is hitting like straight on, right? So this one should be loud too. So then I had a very like simple vector problem right here, right? Because now, you know, how do we solve this? How do we make the sound loud here and quiet here, and it should handle surfaces of any orientation? Well, the way we can start, you know, breaking this down into a mathematical problem is to first realize that both the surface angle, right, and the direction the surface is pointing and the direction you're hitting the surface, both of these vectors matter a lot. So we're going to need both of those. So the direction of the surface is usually modeled with a normal. So a normal is just a normalized vector that is pointing directly out from the surface. So this would be our normal. Okay, and then we have the vector coming in, right? Okay, so well, what's happening here then? We also have the normals of this surface, of course. We have this one right here, which is also the normal, right? So then this basically turned into a very simple case for the dot product. So first off, if you take this vector, for instance, we can first, if we first reverse this one, we can then use it in a dot product. So if you have the normal there, and hold on, let me just erase this vector. That's not how you erase things. Okay, let's model things right here. So if you're flying into this one, I want this to be quite loud. I want this to be even louder. I want this to be pretty silent, right? If you imagine you hit the floor in that direction. And you can see that we're now looking at a situation that is very similar to what we have with the dot product here. Where the closer this one is to being perpendicular, the more silent we want it to be, right? Because we're comparing it against something, some other vector. So again, this is the situation we have. We have a normalized vector. In this case, this would be the normal of the surface, and this would be the vector of the incoming velocity onto that surface, but reversed, right? Because the velocity would have this vector, but if we flip it to the other side, we get this one. So what happens is that if you imagine this being the velocity vector of the object hitting the floor, the longer this one is, the louder the sound is going to be, right? Because then the dot product is going to be 3 at this point. And the shorter it is, the more silent it's going to be. But it's also affected by angle. So even if this one is moving faster, but it's at a lower angle, the dot product is going to end up being lower than this one. So this ended up sort of solving that issue just by simply saying that, okay, audio level equals the dot product of the velocity vector hitting the ground, but negated, and the normal, right? So that was like a very pragmatic use case for the dot product. So what I ended up doing was that again, this is the velocity. Yeah, so the solution for this was simply hold up, where's my neutral color? There we go. So then, let's see, loudness equals the dot product between the normal of the surface, right? And the velocity vector, but negated, right? Because we need to move it in the other direction. We want it to point out from the surface instead of towards the surface. So we negate the velocity vector. There we go. And then that's it. So that was the way that I solved, how loud should this sound be when a thing hits the ground with a given velocity, with a given normal of that surface. So that was a pretty clean way to solve that. And again, it's a pretty clear way of how dot product can be useful. All right, did that make sense? We haven't really talked about velocity vectors, I just realized. I probably should have done that first. But a velocity vector is basically speed, but expanded out into multiple dimensions, right? Or I guess a signed speed instead of a non-signed speed. So if you have a... actually, what's a one-dimensional speed called, if it can be negative?
Velocity. Yeah, it's a one-dimensional velocity.
True, yeah.
Thor, stop.
Right, so a... so say you have the speed of some object, right? Let's go back to our vectors. You can sort of think of speed as like meters per second is a speed because it's how much distance you traverse over some time unit, right? So quite often if you say that something is moving at 2 meters per second, then this would give you a speed, right? But if you want to be able to say that it can move backwards in negative 2 meters per second, this is a velocity, because speed is kind of the length of the velocity, right? So you can expand this into a vector format, just like we expanded positions from a one-dimensional thing into a two-dimensional thing. We can do the same for with velocity. So if you have a rigid body, a physics object in a game, and it's moving by, some speed, then you can represent that using a vector. So the vector is basically telling you how quickly it's moving, or what the rate of change in position is per axis. So if this is a speed vector, then in 1 second, if an object is here, it's going to be here in 1 second. If that makes sense. So this is 1 second, and then after 2 seconds, it's going to move twice this distance. So that's all the way over here. So that would be after 2 seconds, you'd be over here, right? If that makes sense. So this is 2 seconds, and so forth. So this is a velocity vector in that case, kind of interpreted in a vector format. And then if you want to get the speed of this object, the speed of a velocity is the length of the velocity vector. So you can use the same length formula here to figure out the speed of an object if it's moving in 3D, right? Or in 2D or any other dimensions. So yeah, this length formula right here, the length of the actual velocity vector is going to give you the speed of that object, because it tells you how many meters per second it's moving, right? Yeah. Whew. Okay, I'm starting to get a headache, so I should take a pill for that. So I should also drink water. Yeah, do let me know if there are any questions so far with everything we've talked about. Yeah. Are you trans? Yes, I am. Also, that's kind of weird to just straight up ask that, but most people wouldn't appreciate that question. Also, I'll be right back. Where's the... Oh, is it in the box still?
Oh boy.
What?
How do I view their information?
I don't know, actually. I mean, it should be possible. Yeah, most things you get from, like, clicking the name of them, but the DM doesn't seem to have much. Yeah, I don't know. I usually don't see them do much, except when they enter the stream, they always say hi sexy programmer, which is like, you know.
No, that I banned someone who constantly said just that, like 15 times without being banned.
Okay. Huh. That's really strange.
Maybe if they're in chat.
Well, if they're not even in chat, then when did they send the message? Was it like quite a while ago, or?
10 minutes ago.
Gotcha. Okay. Huh. Use the color palette, gave it away. They're almost the flag colors. Sure. Oh no, what happened to my normal? It became an abnormal. I've used dot in the past for an AI to detect what direction the threat is. Yeah, so that's super useful. Like, is something pointing towards something else? That's a perfect use case for the dot product. Again, because that gives you that gives you how closely two vectors are similar to each other. So then, if you want to see if something is pointing towards something else, then this would be this would be the vector towards the enemy. And then this would be the vector that you're looking, right? So then if you're looking towards something, the dot product between these two is going to be 1. If you're looking away from something, the dot product between your view vector and the direction towards the enemy is going to be 0. Or -1, sorry. If perpendicular, it's going to be 0. Yeah, so that's like a very, very nice case for that. Why are normals called, well, normals? Well, they're the normal of a surface, usually. So, but I don't know why surface normals were called normals in the first place. I guess it's because they are, the length of them is set to a norm, I'm guessing. So it probably comes from the word norm, right? Because you have a norm for distance and stuff, right? And the distance is set to 1 on those. I'm guessing, I don't know. How do you rotate a group of points that their origin is not in the center? You mean like rotating a point around some other point? Or rotating a point specifically is a bit involved because it involves trigonometry unless you use like built-in functions for doing that. But generally what you can do is that if you, let me visualize this instead of like talking about it. So say you have a coordinate system, and like you said, you had a set of points, right? Which are vectors, I suppose, but you have a set of points. And then if you, say you want to rotate these as a group, that's sort of what you were asking, right? You want to rotate them around a center point or something. Then a very common way to just like do that in a very easy format is just to take this whole group, take the vector towards the center point, this one right here, and then subtract that from all the points. That will kind of quote unquote move all the points down to the origin. Then you can rotate these points, and then you add that vector back up, and then you're gonna get the rotated around that origin, right? So that's how you would like, you can kind of subtract first, rotate, and then add back, and then you would rotate around a specific point, if that makes sense. So then all you need is a function for rotating any arbitrary vectors, right? So if you have a vector, then you write a rotation function, then you would be able to apply that, but you would do that in local space for all of these instead, right? So it will rotate around that specific point because you did that displacement, right? Yeah. I don't know if that answered the question, but yeah. Quite new to the stream, but watch your YouTube tutorials. Just want to tell you to really keep up the great work. Thank you so much. Thanks for all the contribution teaching people game dev connected knowledge. That's super nice of you. Thank you so much. Heck. Okay. But yeah, if you want to see how to do 2D rotations, Google is much better at answering that question. In Unity, there are built-in functions for that. There's like a vector2.rotate, I believe. Yeah. Okay, should we move on? Are there any questions about the dot product, by the way, or something related to this that we should talk about? The formula is, yeah, that looks correct. Although you need to mark what x coordinate, or no, yeah, you have the x coordinate. Yeah, that looks correct. The thing I like never remember is the signs of those, like which one should be negative, which one should be positive. But it looks correct, yeah. Yeah, if you just search the internet for like 2D rotations, you're gonna find those Stack Overflow posts or whatever, and you're good. Yeah. All right, we've extended the blackboard. All right, no more questions about the dot product. Neat. All right. You know what would be funny? If I talked about trigonometry and angles without ever mentioning pi, I might actually do that, because pi is more confusing than helpful. Let me think. I have very strong opinions about pi. Pi is pretty awesome, though. It's wrong. It's close to being correct. It's very close. Yeah, actually, let's not use pi. It's garbage for educational purposes. Okay, we're going to talk about angles and trigonometry. So angles and trigonometry, you don't always use that, but it's a pretty useful tool. Whenever you want to make something in a circularly arranged things, or you have some triangle and you want to get some angle from that, or some length of one side of the triangle. Sometimes you do need trigonometry for that type of stuff. So okay, we did talk a lot about vectors now, right? So now we have some knowledge about how 2D vectors work. And we also talked about normalized vectors, where the length of the vector is exactly 1, right? You sound irrational when you talk about pi, god damn it. All right, let's make another coordinate system, because we just love coordinate systems. Let's see. We have to ratio out our pi talk. Hold on. Okay, that's probably good enough. You need a coordinate system Photoshop brush? That would be nice. Okay, we got a coordinate system. We've got the y-axis, we've got the x-axis. We have, these are both the length of 1. So again, this is a normalized system. So this is 1, 1, and again, 0.5, 0.5, and so forth, right? Okay, cool. So now we're going to talk about the sine and cosine. Actually, we might want to talk about angles first. No, actually we don't. Never mind. We don't need that. Who cares about angles? All right. Now I'm gonna do a scientifically correct circle this time. You ready? Oh jeez. There we go. My scientifically correct circle now made my arrows look very scientifically incorrect. So I'm gonna move this one. Perfect. Is that visible on stream? It's visible on stream. Good. Okay. It's a bit faint, so... also, I'm gonna... there we go. We need this one for colors. All the variates. Okay, so sine and cosine. You're familiar with angles, right? You have quite often you have like two vectors, and then you can get an angle between those two vectors, right? So sometimes you call it alpha. You can call it whatever you want. The name of the angle doesn't really matter. So you have some angle, right? This one would be about 45 degrees, right? If you measure in degrees, which is, 360 for a full turn, 90 degrees for a quarter turn, 180 degrees for half a turn, right? Okay, so you got 45 degrees here. So you can use angles in different formats. We're going to talk about that very soon, but for this example, the angle doesn't really matter, or what type of angle unit you're using. Okay, so let's talk about trigonometry. So if you want to get a vector given a specific angle, say you have like some sort of game where you're gonna launch a projectile or something, and all you know is the angle, right? So how do you get the direction based on that angle? That's something that trigonometry can help you answer. So let's say you have this angle right here. You have a vector pointing like this, and you have this obviously has an angle. Let's call it alpha. Now, what happens is that you don't have this vector. You have an angle, but you don't know what direction that one is going to point. So how do you get that angle? So this is, or how do you get that coordinate? And this is a case where trigonometry is going to help you. So if you take this point right here, we need the x and the y coordinate, right? Where the x coordinate would be this distance right here, right? And if you have the y coordinate, that would be this distance right here. So these are the two values we need. And then the way to get those two values is actually very straightforward. So if you want to get this distance, you do the cosine, which is a function, and you do the cosine of alpha, and that gives you this length. And if you do the sine of alpha, that's a weird n, you get this distance right here. That's a very, very basic way where you can use sine and cosine to get a two-dimensional vector. So if you remember the dot product where we were projecting points onto something, the sine and cosine can sort of help you do that too. But instead of doing that with, two vectors, you're given an angle. So sine and cosine helps you with angles and coordinates, right? So they're basically angle utilities. So what you can try to remember that cosine gives you the x coordinate and sine gives you the y coordinate. That's kind of how I try to remember which one is which. Just cosine is x, sine is y. Yeah. Another cool property of normalized vectors. What part of it? Okay, all right. So did all of this make sense so far? And again, the angle can be any unit of angle. It doesn't really matter if you're using radians or if you're using something else. Being able to decompose sine and cosine from the xy of the vector itself. Yeah, so you could actually do the other way around. Yeah, let's say you actually want the angle based on that vector. Although that would, let's see. Could you do that? I think you can, but wouldn't that be wouldn't we have to set up an equation system? Because there's the atan, but I feel like atan is a bit esoteric at this point, because we haven't even talked about tan yet, just sine and cosine. Um, anyway, because basically okay, we can talk about the inverse operations of sine and cosine. They're pretty useful. But the issue with that is that you tend to have multiple answers, so it becomes a bit more complicated than one might think. But okay, so let's look at this one where we have the sine of some angle gives us a y coordinate, right? So if we write that out as an equation, we would get this part right here. So sine of alpha equals the x coordinate of the vector, right? Or no, sorry, the y coordinate. All right, so now I have a way to get the y coordinate. Now, what if we had the other way around, where we want to know what angle a vector would have if the y coordinate has a given value, right? That's something you can ask yourself, right? So if you want to do that, then there's an inverse operation of sine, sometimes called like arc sine or asine. So either asine or arc sine. You can also call it, sometimes you write it as sine and then -1 or raised to the power -1, kind of like a inversion type of thing. Yeah, so all of these are ways you can write the inverse operation of a sine. Anyway, usually in video games or in APIs or whatnot, they use asine like this. So we're going to call it asine. So if you do the asine of a sine like this, they cancel out theoretically. There's some nuance in that, but so generally we can transform this whole equation into the angle alpha equals the asine of y. So if we want to get the angle, we can use the inverse sine in order to figure that out. But one thing that you should note about this is that there are two answers to this question. So if you note that you have sine and you have the cosine, right? And given an angle, you get a specific value for both sine and cosine. But if the sine is supposed to just give you this value right here, you'll also maybe have noticed that this value over here also has the same sine value of that alpha, right? So if you do the vector here, this one has a different angle, right? This one has an angle that goes all the way from here out here, if that makes sense. Actually, I should do that one in purple. There it is. No. Stop. I did an incorrect. All right, so this vector right here has a different angle, but it has the exact same sine alpha value, right? You kind of have an ambiguity. So you kind of get two answers from this one. Technically, in code, you tend to not get multiple answers. Most of the asine functions give you one answer, and I think most of them usually just give you the positive angle in case there are negative ones and whatnot. So whichever one's is closest to 0 and not negative. So yeah, the asine function is not perfect because you can't really get both answers out of it usually. So there is a helper function that's very, very common in graphics, very common in games, called atan or atan2, which is we haven't talked about the tangent and the arctangent, but atan2 is kind of a bit different. You can kind of think of it as a video game specific or rendering or programming specific trigonometric function, where this one you can apply this one to a vector. So we can give that one this entire vector. Usually they have it in the flipped order where y coordinate is first and x coordinate is after, which is weird and I don't know why they do it, but that's quite common. Anyway, so if you do atan2 of this one, that's going to give you a single answer for the angle. So a tan2 is usually the one you want to use if you want to get, given a vector, what angle does it have in relation to the to whatever reference vector they have. In this case, we used the x-axis as a reference vector because they're all like relative to that. Because angles have to be relative between two things, right? Yeah. Okay. So we haven't talked about tan because it's, we could talk about that as well, but generally I pretty much only use the tangent when doing like triangles and I do figure out the hypotenuse or something, which is very rarely used. But I guess we can do it for completeness. I can just mention what value that gives you. Is that layer empty, really? Okay, there we go. Okay, so how do we get the, so what's the third function, tan? So tan stands for tangent, and you can think of, if you have so we talked about normals, right? We talked about this one right here. A normal of a surface is a vector pointing straight out of the surface itself. A normal tangent to the surface is this vector right here, right? Or a vector like this. Both of these are tangent because they go along the surface instead of pointing straight out from it. So this would be our normal, and the blue vectors down here would be the tangent. Okay, so tangent is something that is tangential to something else, right? And that is why it's called, I'm pretty sure that's why it's called tangent, because the tangent function gives you a line that goes from, you can imagine this point right here, and you have the circle right here, right? A tangent to the circle would be a line like this, right? And if you draw that line, it would hit the, there we go. It would cross this line somewhere, right? Like the x-axis, like this. And this intersection point and this point right here, if I just erase the clutter, then there we go. The length of this one, this vector, that is what you get if you do the tangent of alpha. So you get this one from the tangent of alpha instead of, the x and y coordinate here. So you get the length of this vector. It's super useful in various cases. When it comes to like triangles and stuff like that, I almost never use it anywhere else. By far the most common functions I use is the sine, cosine, and a tan2, especially when doing shaders. But the most common ones are sine and cosine. You can get very far just by knowing these two. Yeah. So also tangents has this interesting property where, since this is kind of an intersection with a line here, if you move closer here, the tangent is going to be like starting to, it kind of has this shape, right? But the higher you go, it's going to extend to be extremely long, right? And as you approach this point right here, the tangent is going to shoot off to infinity. Because it never intersects here. And the length of this one is just like, it doesn't have a proper length. It's just undefined because it never reaches an end. So that's why the tangent of 90 degrees, for instance, is just undefined. Or if you want to, it would be kind of like positive infinity or something. But yeah, so if you look at a graph of these functions, you would get the sine wave would go like something like this. The cosine would be slightly different. So it would be like slightly offset, but otherwise the same. Has the same shape, right? But then if you look at the tangent function, that one just like goes crazy. It's like, it's pretty low here, then it shoots up to like infinity, or like positive infinity, and then it comes back from negative infinity. And then it shoots back up again like this, and then it flips around again and comes down like this. And that's because again, if you look at the geometric example, you can see that this line is intersecting. You know, the x-axis has a pretty short length here, but as soon as you start hitting 90 degrees, the length of this one is going to be extremely long, right? So that's why you get this like wonky graph where the tangent of the function just looks very, very strange, right? Yeah. Okay. I hope that made sense of the basic trigonometric functions. Another super useful case for trigonometry is that if you have a triangle, say, of a 90-degree angle, trigonometry can help you figure out various properties of this one. It's super, super useful for that. Yeah, usually you have an angle alpha here. Hello, vehicle. And then given this and a few lengths, maybe you know the length of this one, let's call it A, and you want to figure out, you have this angle, you have the length of this one, and you want to know how long this one is, you can use trigonometry for that. So whenever you have a triangle and you want to figure out either an angle or a length of some side, the trigonometric functions are going to help you there. Yeah. Instead of using sine cos for their point, could you just rotate the coordinate axis and multiply points by them? Yes, you could do that, but rotating the coordinate axes themselves would require trigonometry. So yeah, but you could do that. Yeah, if you have a case where you can rotate it without using trigonometry, then yeah, that could help you with that. As long as you don't make sure you don't execute too much code or something, because rotation updates something else or whatever. Yeah. Okay. But yeah, I'm not going to go through all the different ways you can use sine and cosine and tangent here. You can find that online. Yeah, usually you define it like you have an angle, then you have an adjacent side, and you have a hypotenuse. The hypotenuse is the of a right angle triangle. That's the longest side, usually the diagonal. And then you have an opposite side. And then using trigonometric functions, you can figure stuff out from there. So you have, if you do say the sine of alpha, sine of alpha is the length of the opposite side divided by the hypotenuse, I'm pretty sure. The cosine of alpha is the length of the adjacent side of the triangle divided by the hypotenuse. Again, there we go. Then I have the tangent of this one of the angle equals the opposite divided by the adjacent one, I believe. There we go. So these are relationships that are super useful. Yeah, so given these, you can figure out a lot of stuff with this triangle. So what you need to do is just plug in the known and the unknown values and then shuffle things around until it works, right? Say you don't know the angle. You don't know the angle, but you know the hypotenuse and the opposite. If you do that, then you can use this function right here. So this is unknown. Hypotenuse and opposite are known. So you can plug in the known variables here, and then you do the again. You can kind of flip this around. So then you would do the a sine, which is the inverse of the sine of the opposite divided by the hypotenuse, and then from there, that would give you the alpha angle, right? So again, you can like shuffle these around just like you would do with any other formula, right? So just plug in your unknowns or plug in your known values and then figure out the unknown value. So if your angle is unknown, but you know the length of this one, you know the length of this one, you can use this function to figure out the angle. And you can do this for all of these. It's super, super useful. But yeah, you can read about that like pretty much everywhere you can read about trigonometry. Like the Wikipedia page on trigonometry has a lot of these, a lot of information on this in case you want to get more info. Yeah. Whew. I feel like I haven't talked about this in practice very much. This has been very theoretical, but it is a lot of theory, I suppose, in math. But yeah, I did mention the thing hitting a surface and then setting the audio volume of that, which was one use case for the dot product. Or like seeing if something is facing something else, for instance. All right, so let's see, what do we do next? We've actually talked about this one. So sine and cosine, we also talked about the tangent, that's neat. A10, not really, but we talked about A10 too. Glad you like the math, Brilliant. We have not talked about angles and radians, or we haven't talked about tau either. Heck, I need to drink more water. How's it working out so far, by the way? Am I like going too slow? Am I going too fast? Is there anything you feel like I didn't cover that I should cover? Do let me know if there's, yeah, just feel free to just tell me to clarify something if I wasn't too clear about it. Also, thank you so much for the follows. I haven't been thanking everyone who's been following. I'm sorry about that. Using different colors is really great. I'm not very consistent with my colors though, in terms of like using one color for one specific thing, but anyway. Okay. I like to use black paper sometimes and colored pencils. I actually, yeah, I have an example of some math, or geometry rather. Heck, where did I post it? I'm gonna find it. It's gonna be somewhere media. Rapidly going backwards in time right now. Where is it? Oh, here it is. This is, I don't have any like black paper and color pencils I can use for that. But I use a, I have colored pencils too, which are super useful. When I was in Japan, I found this like place that had so many pens, like ballpoint pens, and you could like fill them with colors. So I found some that could like fill, I think it was like 5 colors per pen, which was super, super useful. And they looked nice. They wasn't like kids' pens that are like super thick and bulky. They're pretty like slim and useful. So yeah, I usually do like mathematical notes and whatnot on paper like this, because it's, yeah, it's very like, it's a more descriptive way of doing it, because then you can mark stuff and like kind of associate things in a better way without having to remember every association, right? Yeah, anyway, yeah, it was kind of an interesting case. Someone asked like, how do I get the, if I have a spline that ends somewhere and I want that spline to to do a circular arc onto a point, how do I get the origin of that circle? That was kind of the question that I was answering with this. But yeah, if you want the the Twitter thread, feel free to read up on it. Anyway, this is not really like this is not really running numbers in math. This is more like specifically geometry, right? Can you show us the pens? I have one of them. I lost the other one, which is really frustrating. Right. This one is closer to your standard like 4-color pen thing. This one has like your your different colors. You got red, green, blue, black in this pen. But this pen also has a what's it called? I don't know what this is called. The non-ballpoint pen. Ashley, do you know? What's this type of pen called when it's not ballpoint? Pencil is the name, yeah. Yeah, a pencil. There we go. Yeah, so it's also got the pencil, so you can like use this as a regular pencil if you pull the this little tab thingy. It's super useful. Yeah, I love this pen. Anyway, that was the one that you couldn't really fill. But then there's this one. This is one where you could fill with custom colors. I don't know if you can see because of the reflections and whatnot, but I have a few different colors in this one. Yeah, so this is the one that's supported 5 colors, and you can see that it's got these like 5 separate little levers that you can pull. So you could like replace this one with like any colors. So yeah, this is the one I got in. I got both of these in Japan. The brand name, Style Fit Meister is the name of this pen. Yumi Style Fit. Yeah, I don't know. I don't know if it's where it's available. I mean, it's probably a brand that you can get anywhere. That is, yeah, I don't know. I'm guessing it's not like unique to Japan, so. But yeah, they're super useful. I love them. Had one that came with like 20 colors. I'd love to find one that has like a ton of colors, but I want them to like, I wanted them to not be massively thick. Any particular math books you can recommend for game dev? Not really. I guess the best math book for game dev, I would say, would be to make games. Like, as soon as you run into a problem, read up on it. Like, that's kind of the way that I properly got into math, because, like, for me, it's hard to learn something if I'm not interested in that thing. But if I'm making a game and I'm interested in making a game and something is stopping me from that, then learning that something, that's nice. Like, then I can feel like more motivated to do it. So I'd recommend like start making a game as soon as you find an issue that's like seems related to this, of like, oh, this thing is supposed to point towards this thing, then heck, how do I solve that issue? How can I break this down into a mathematical problem? And if you don't know that, then you have something new to learn, right? And that's going to be directly applicable to the stuff that you're doing, right? Otherwise, I don't have any specific recommendations. What's your opinion on Writer ReSharper? They seem to be very good. I don't use them myself, so I can't really say much about them. I wish Writer was cheaper. That's all I can say about Writer. I just use Visual Studio. What kind of flight sims do you fly? I fly no flight sims at all. The controllers are my girlfriend's. So she's the one who's doing the flight sim stuff. She might still be in chat. There she is, Kyperia in chat. There are books that use things like case studies to learn programming, give them math. That's good. Nice. I don't know any of them, but yeah, feel free to mention them or link them if you want. Can I really understand stuff while I'm making if I don't know the fundamentals? Like, I know calculus and stuff, but I'm weak at trigonometry and geometry. I feel like if you Google for, like, how do I get the angle toward an enemy, for instance? Then you're probably going to find some resources on some techniques to do that. And those techniques are going to contain things that you haven't really learned yet. But hopefully the stuff that I'm going through now is enough of a fundamental base so that you can continue learning the things you need to do for your projects, right? But if you're starting from zero, then of course that's going to be difficult. Then you need to then you would need to learn the fundamentals somehow, right? There's any way to watch your stream from yesterday? Do you upload this to YouTube or something? I do upload them to YouTube. It takes a while to get it up there because I need to edit the video and whatnot. Twitch also stores my streams for a few, like 1 or 2 weeks. The problem with Twitch though is that Twitch is going to mute certain sections that contain copyrighted songs. So you can get the VOD for the previous stream, but it's going to have muted sections, and you're probably better off waiting for the YouTube version in case you want one that's not muted anywhere. All right. Also, if you want, if there's a specific issue in game dev where you this seems to be related to angles and vectors and whatnot, we could try to solve that live on stream if you want to, if you can think of like a math problem or a geometric problem like that. Anyway, I need to drink more water, then I need to go to the bathroom, and then we can continue. Do you have plans to work on that procedural multiplayer flight simulated with Ashley? You remember that? You remember Flything? Fogsight remembered Flything.
Hey!
Heck yeah. I mean, we don't really have any strong plans on working on that. We have like ideas and things we would like to do in case we were to continue working on it, but we haven't really solidified that. But maybe, yeah. I mean, I think that the base of that game works really well. It's less so as a multiplayer game and more so as a meditative single player thing. So it kind of depends on like how we would, what approach we would have. But and something that you probably know a better way to deal with it. I was working on a tool for a designer that basically scales the cube based on an aspect ratio. So my problem was the hierarchy was all scale and rotate in all possible ways. My first study was using matrix. Right. I mean, the reparenting thing, I guess that sort of works. But it would be pretty similar to the first issue we had, right? With the health bar situation. But, sorry, instead of a single scale, you would have... No, actually, you would have a single scale. Or no, you would have 2 scale values and then pick one of them. But it would basically be the same problem, but this would be with the rotations and possibly trigonometry, and then also figuring out these scales on a per-axis basis, right? Because usually with aspect ratios, if you want to fit something to some, specific aspect ratio, you would have to, you generally have to what scale value do I use to fit vertically, and then what scale value do I use to fit horizontally, and then use the minimum of those 2 values in case you wanted to be fully within the bounds of that aspect ratio. So usually you need to calculate 2 values when you do those types of aspect ratio shenanigans, if that makes sense. All right. Let's see, what next? Angles. Should we talk about angles? Yeah, we should talk about angles. If you want to use trigonometric functions, in Unity, you're going to see a chaotic mess of some functions using angles in, 0 to 360 degrees, right? Some of the functions are going to use radians, and then you're going to be like, what the heck are radians? So how does this work? Let's actually talk about angles. I feel like that's very, very relevant. I remember when I was in school, my teachers, I seem to remember that they were really bad at explaining specifically the trigonometric functions and radians. They just totally did not help me understand those concepts. Yeah. What do you mean that area is empty? You're empty, Photoshop. There we go. Do you need an angle on angles? We're gonna get to that. Sorry, just have to move things around on this very crowded blackboard. Hair looks so kawaii. Thank you. I do appreciate my hair. I like it when I've like curled it like 1 or 2 days ago, and then you get these like wavy things. I love it. It's super nice. Okay, angles. Let's talk about angles. How does one angle? All right. Trying to figure out where to start. There are multiple approaches we can have. Which approach has the least amount of dependencies? Okay. Let's start with degrees. We're gonna that's the angle I'm gonna take for talking about angles. All right. Why don't I do the entire axis at once instead of like... I should just make a cross. Like, what am I doing? There we go. I'm gonna shorten it a bit. This is not perfectly circular. But you know what? It's okay. Okay. See you guys. Hope to see you bot on YouTube. Alright, thank you so much for joining, Interpol. Super nice to have you here. Alright. Let's talk about angles. So, in many cases, you tend to use degrees. That's probably the one you're most familiar with. That's kind of the angles you use when starting out to learn about angles. So usually you have some sort of coordinate system. Quite often in math, the angle in which things are relative to is the x-axis. So if you have the x-axis here, and you have some other thing, like a vector or, you know, some side of a triangle, if you want to get the angle right here, you would specify that usually in degrees. So in degrees, this would be approximately like 45 degrees. And the reason it's 45 is because degrees have sort of been like axiomatically just defined as 0 degrees here. And at when it's perpendicular, that's 90 degrees. When it's fully opposite, that's 180 degrees. There we go. 3/4 is 270 degrees, and so forth. And then a full turn is the same as 0, but you can also call it 360 degrees. So, okay. So this is kind of the standard way of defining angles colloquially, right? That's kind of a 90-degree angles. A lot of people are familiar with what that means. That's a right angle that's fully 90 degrees, and that's a quarter of a turn, right? All right, that's one way of defining angles. Now, this is not the way you generally define angles within mathematics. So in mathematics, you usually use a different type of angle called a radian, or a unit of angle. So let's duplicate this one. And now we're going to do radians. But first, before we do that, what the heck is a radian? And how does it relate to a circle? Well, just going to clear this out. There we go. Actually, I need to clear a few more things. Don't switch tools on me, Photoshop. Trying to think. Right, okay. Radians. Here we go. Let's grab the circle we had for the other one, the other coordinate system, and use that one and this one too, because this is pretty important to get right. There we go. We need to extend this one a little bit. Wrong color. I was pretty close with my axes this time. I'm pretty happy. Okay, so now you can see the circle here, right? So let's add a little outline to this one. What is happening? Why did Photoshop open help links that are broken? Okay. What the when I press 1, what is happening? Okay, I didn't press F1. That's the thing. I didn't press F1. I'm really confused. I did have a function modifier, but pressing 1 shouldn't become F1. I'm really confused. Okay, there we go. We've got a circle in a coordinate system. That's great. I just need to make sure I don't get this incorrect. Yes, okay. Let's go to a different layer because we don't want to draw on the same layer. There we go. All right, say you have a circle and you want to invent a new way to measure degrees that can be like super nice and convenient in a lot of equations. Turns out a lot of equations become way simpler if you define a degree system or a system of angles, a unit of angles called radians. And then, so instead of going from 0 to 360, you have another unit in radians, and so then we need to define what is 1 radian. Like what we have, 1 degree is a specific angle, right? It's a very small angle, and this would be 1 degree, right? So 1 degree, so because we kind of need to know, what is the unit we're working with? So this is 1, right? Okay, so if this is 1 degree, what is 1 radian? Well, 1 radian is where if you imagine the radius of this circle, if you take the length of this one and then you kind of like bend it up along this thing right here, you kind of like take this radius, then you squish it up towards the edge of this the circle, then what you're going to end up with is an arc that goes some length, right? So this one is the same length as the radius. The arc length of this is the radius, right? And then since it's the radius, that's a distance from the center to the edge of a circle, right? So this is also the radius. So you have the radius and you have the radius here. And then this segment right here has an angle. So we're going to define this angle as 1 radian. 1 rad.
That's pretty rad.
It is pretty rad. So this is how radians are defined. So if you have a circle with a given radius or a unit circle, then 1 radian is the angle you get when you take the radius, squish it up on the arc, and then the angle you end up with, that's 1 radian. And this is not exactly like 45 degrees. It's slightly, I forget if it's less or more, probably more. Yeah, so okay, so I have 1 radian. And then we can ask, like, what is 1 full turn in that case, right? Has someone straightened the site to know it's 1 radius? What do you mean? All right, anyway. So it turns out if you define this as 1 radian, then you might ask yourself, what is a full turn? Well, usually in textbooks and in math class and absolutely everywhere, they usually define a full turn in radians is 2 multiplied by pi and the unit is radians, right? So this is a full turn. 2 pi radians is 1 full turn in the angle unit of radians, right? So then 2 pi is 1 full circle. If you want to go halfway, that would be, you know, pi radians. Or as Dinos is saying, 6.28, right? Because pi is a constant. It's a shitty circle constant. But let's just say it's 6.28 something, 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 right? It's a very long number. Incredibly long number, in fact. Okay, so this is 1 full turn then. So that's pretty neat, right? So now we have a weird angle system where instead of saying it goes from 0 to 360, then this one goes from 0 to 6.28, yada, yada, yada. That's useful, right? You might not know why it's useful, but it does simplify a lot of equations when you use radians. So then I might wonder, like, how do we use, it's kind of difficult to work with radians because you're like, well, what's a quarter turn of, what's a quarter of 6.28? So I mentioned pi before. Well, pi is a garbage constant, so I'm going to explain why. So we're going to talk about tau. So the constant tau, pi, the constant pi is usually defined as the ratio of the circumference divided by the diameter. I'm pretty sure, right? Yes. So this is how you define pi, usually. And this is true for all circles. And pi is usually a value of like 3.14 and so forth, right? So anyway, as you can see, pi, this value right here, is half of a full turn in radians, which is kind of strange. Like, if you want to use the circle constant in angles, defining a full turn as 2 multiplied by that constant is really confusing. So one problem that you run into if you want to measure angles in radians and you're using pi, then what happens is that so you want to like try to figure out what's a half turn. Like, half turn is pi. Okay. What's a quarter turn? Well, that's pi divided by 2. What's a full turn? And then it gets like messy, right? Because then it's like, oh, geez, okay. So it's like 3 quarters, and then that is multiplied by 2 pi, right? Which is 6/4 of pi, yeah, and so forth, right? Which is, it gets messy, right? Anyway, and that's really shitty, because like, you're like, oh heck, why do I need to keep caring about this too? So, what we're gonna do is we're gonna say fuck pi. Pi is a garbage constant. We should never use pi again. We should just throw it into the bin of history, put it in a museum. That's where it belongs. It should just sit there somewhere and be like, hey, look how dumb people were back then when they defined constants as shitty values and made all equations in the entire world garbage. So we're not gonna use pi. We're gonna use a different constant, and it's gonna be called tau. So tau is a proposed circle constant. It's not fully accepted within, you know, mathematical communities, but it's incredibly useful for like angles and stuff like that. Makes a lot of equations simpler. So we're going to define tau as 6.28 and so forth, right? So instead of being the ratio between the diameter, or the circumference to the diameter, we're going to define tau as the ratio of the circumference to the radius. And this is so much better as a circle constant. This one is going to make every single equation so much better. And if you look at, you know, how would you define radians then using tau? Well, using tau, then a quarter turn with tau would just be tau divided by 4, right? Half a turn would be tau divided by 2. And 3/4 would just be the 3/4 multiplied by tau. It's very, very simple. If you want to go 75%, or if you want to go, I don't know, any percent around this, you know, 75% would be this one. So you can just say, you know, 0.75 multiplied by tau, and then you get your 3/4 turn. Then you're 75% across the whole circle. So generally, when I deal with angles, I pretty much always use tau because it makes things so much easier to understand. Otherwise, you're gonna have this weird 2 that's like slapped in everywhere, and it's just so confusing. Tau is then a value that is exactly equal to a full turn in radians, right? Which is super useful. So then you can easily get like quarter turns, half turns, and so forth, or whatever percentage around the circle you want, right? So as a rule of thumb, tau is also exactly equal to pi times 2. So whenever you have pi times 2 somewhere, you can just replace that with tau, and you would get the exact same equation. Yeah. Okay. What's the issue with tau for not being properly accepted? Probably because pi is incredibly established. It's very hard to change it because it's like used in so many places. I think there's been like one paper or something that used tau instead of pi, but yeah. Okay. Tau equals radius times 6.28. No, that is not correct. So tau is a constant. Like tau always has the same value, right? It's not dependent on the radius of the circle or whatever. Just the same way, if you have a circle here and you have an angle of 45 degrees and you make that circle bigger, the angle is still going to be 45. So nothing changes with that, right? So the angle is just completely independent of the radius. So yeah, tau is a constant. It's always equal to 6.28 something, or you can say that it's equal to pi times 2, or you can say that it's a ratio of the circumference to the radius, right? And this ratio right here is always equal to tau as well, regardless of the radius of the circle. Also, you're not weird for liking math. Math is hecking awesome. Yeah. Okay. Cool. Did that make sense? So basically, if you want to measure things in radians, then tau is a very useful constant because then that helps you kind of easily say what's a half turn. That's tau divided by 2. You could run the numbers yourself and just have 6.28 and try to figure out the what that is divided by 2. But it's easier just to use the constants, right? So now we have a unit of angles, and it's 6.28. So we get like 6, 1, 2, 3, 4, 5, 6, and a little bit more amount of segments like this, right? Throughout this whole thing. 1, 2, 3, 4, 5. I did not do this properly. Well, there we go. You have like segments of this. So the full turn would be 6.28 radians, right? Yeah. So if you ever do something in Unity where it's like Unity Euler angles, for instance. So if you want to set the Euler angles of a transform, then always check the unit it's using. This is going to mess you up if you don't check the units. So in this case, there's a function in transform called Euler angles, and it tells you that it gives you the rotation in degrees on this one. So always make sure that you know the unit of the thing you're either getting a value from or setting a value to, because all of these functions they're a bit mixed up. Some of them use degrees, some of them use radians and whatnot, right? So for instance, the math function for a sine in Unity, this one needs it in radians because it says input angle in radians, right? Yeah. Okay. So be careful what the input unit is and the output unit. That's super important in order to properly be able to use these trigonometric functions. Super hydration bot. Heck. Thank you so much. I should have had at least 360 milliliters. How much have I had? I think I've had approximately 1 full bottle, in which case I've had 650, which is so we're good. We Gucci. I love that expression. It's definitely Ashley's fault as well that I'm using that one. It's pretty Gucci. Okay, any questions about this so far? This is pretty involved and it can seem pretty esoteric because it's kind of like, why do we use radians? It seems kind of pointless. But it's actually not, because it simplifies a bunch of things. But I'm not going to go through all of those bunch of things because A, I don't know them, and B, it would take a lot of time and I would need to read about it and so forth. Yeah. I guess no questions about that. Super clear. Everybody's fully on board with Radians and Tau. Awesome. Does anyone still support pi instead of tau? If so, I will debate you. Where are we? Let's see. We're talking about angles, radians, tau. Is tau useful in game dev? Yes. It's useful wherever you would use pi. And you use that type of stuff in game dev, so yeah. Pi is a fun thing as it's an infinite ratio, but so is tau. Any argument you can give to pi, you can pretty much use for tau as well in that case. Except tau also simplifies a ton of equations compared to pi. Yeah. Now we just need to name some food after tau. Hey, on tau day, you can have 2 pies instead of just 1, right? Should have called it like cake. If a library doesn't have tau, you can easily define it. Yeah, tau is just a number, right? So if you go to Google and you do tau times 1, because Google has support for tau. So if you do tau times 1, then you get the actual value of tau. So there we go. This is the full turn of an angle measured in radians. That's this value right here. And that's equal to tau, which is equal to 2 pi, right? Okay. All right. How are you feeling so far? Was it too much? Too little? I don't know for how much longer I can stream. Heck, I might need to divide this up into multiple streams. Actually, there's not that much left to talk about, I think. So we need to talk about space. That's one of the most important things that we probably should have talked about earlier. Space is probably more important than trigonometry. Rotation is more like practical stuff and like how you use rotations. Not sure if we should talk about that. Derivatives can be useful. Cross product, I'm not sure where to. That would be go with rotations, probably. This video go to YouTube later? Yep, it will. This will be on YouTube. Wait, why did I? Oh, right. That one also had the flag in it. Delete. Cross product is related to dot product, right? Not really, no. They are operations you can do on vectors. Specifically, the cross product is for 3D vectors. Because usually the problem quite often is that I don't like the way people frame this, but people can, actually, let's just talk about the cross product. Let's do it. Okay, so the in-game dev, or in 3D space, you have 3 axes, right? You have the x-axis, you have the y-axis, and you have the z-axis, right? And you tend to color code these with red, green, and blue, right? So let's draw these axes. So let's see if we have a... I want to make sure I get this right. you have the x-axis, and then you have the y-axis. Y-axis is usually the one pointing upwards. So in Unity, y is up, and Unity is also a left-handed coordinate system. So that means that if you do this shape with your hand, you have x, y, and z. And if y would be pointing upwards, you have the coordinate system in Unity. So in my case here, the z-axis would be pointing away from the camera here in Photoshop, right? So this one would be the z-axis. Okay, so what does a cross product do? Well, the cross product will give you a vector that is perpendicular to both vectors you send to the cross product. And the length of the cross product is similar to the dot product, where the you can kind of get how similar those two are. But cross product has another property that is super useful. Heck, my voice is getting hoarse. I'm sorry. Okay, so say you have a vector in 3D space now. So again, it's 3D, not 2D. So now we have, we're working in a different, we have another dimension now. So let's make a vector that is flat. So it doesn't have any component on the y-axis. So this vector, say, is here or something. Or it can be like, you know, on the ground, you know, of the circle here, if that makes sense. Hold on. So this one doesn't have any y coordinates. It's just got a z coordinate and an x coordinate. Hold on, I'm trying to find a good vector. So the z coordinate of this one would be like that. The x coordinate of this one would like relate to that right there. Because you can imagine these axes continuing like this, right? Okay, so we got a flat vector there. If you take this vector and then you take another vector that is also on this plane down here, then if you do the cross product between these two, say you do the cross product between this one, no wait, if you do the cross product between this one and this one, so let's call them, well, we don't need names for them. If you do cross between that one and that one, you're going to get a vector that is pointing upwards. Because you get a vector that is perpendicular to both, which means that it has to be at a 90-degree angles to both of these vectors down here, right? Otherwise, it's not going to be perpendicular to both. And for any two vectors, unless they're like in a degenerate setup, you can get a perpendicular vector to both. So for example, inside of, or in Unity, if you take this coordinate system where you have the three axes and you do the cross product between x and y, you get the z-axis, right? So whenever you have like vectors that are tangent to some surface, you're going to get the z-axis out of that, or, you know, a perpendicular one out of that. So, you know, cross product between x and y is z. Because if you, again, use your left hand, x, y, result of cross product. Or, you know, first parameter of cross product, second parameter of cross product, result of cross product. If all of these are normalized, if they're normalized and the input components are at a perpendicular angle, the output is also going to be normalized. But that's not always true though. So if you take the x dot product between let's see, x and okay, dot product between z and x. So maybe I should write that. So dot product of z and x equals y. Okay. So there are some interesting properties with the dot products. So if you, for instance, take this very same equation and you, wait, did I say dot product? I meant cross product in case I did. What do you mean empty? You're the empty one, Photoshop. You don't have a soul. That's pretty harsh. I'm sorry, Photoshop. So if we reverse those two, then what's going to happen is that the vector we get as a result of that is going to point in the other direction. So in this case, we would actually get the negative y-axis. So this can actually be pretty useful to, for instance, do you check angles between things and gets the sign of some relationship between two vectors. So you can sort of imagine this where the vector we get out of the cross product, this one can change length if these, oh, sorry, cross, heck, yes. There we go. Thank you for letting me know. Sometimes it's hard to like think and talk and draw at the same time. But anyway, cross product. There we go. Now it says cross. Thank you. Sorry about that. Right, so if you do the cross product between the x-axis and the z-axis, and say you move the x-axis, so instead of it's pointing this way, you move it closer to the z. You kind of like rotate it on this plane, right? What's going to happen is that the resulting vector is going to be shorter. And the closer you get to z, the shorter the length of the result of the cross product is going to be. And as soon as you pass to the other side of this plane with that axis, then it's going to be starting to point downwards. And as soon as the first input is pointing directly opposite, it's going to be completely negative, which is equivalent to this case right here. So you can kind of imagine this one like moving downwards as the vectors become more similar, and then as they pass, you're going to get a flipped sign on that one, which is a very useful property. So from that, you can then kind of see on what side something is of something else, which is a very, very common use case for the cross product. You know, what side of something is this other object? Yeah, that's a nice little use case. Yeah. All right, that's the cross product. It gets more complicated in higher dimensions, but we're not going to go there, I suppose. Yeah. All right. That was the cross product. A very simple explanation, I suppose. Except that I kept writing dots, so you had to be like extra careful to make sure that you can translate from my shitty typing to the correct typing. Yeah. What about A10-2? We've already talked about A10-2. That one's down here. So A10-2 is sort of a way to get the angle of a two-dimensional vector with relation to the reference vector pointing to the right. So if you have a normalized vector, or any vector in A10-2, I think, like a vector like this one, and you want to know the angle, A10-2 is going to give you that angle. So yeah, that's what A10-2 is. Okay. Oh, so the one thing I don't like about how some people frame the, what's a normalized vector? A normalized vector is a vector of length exactly 1. And those vectors are super useful for a lot of different things, because a lot of operations have very specific and useful behaviors if you give them normalized vectors. Yeah, and that's it. The length of the vector is 1, and then it's normalized. So if you have a vector and the length is not 1, and you normalize it, you keep the direction, but you make the length of the vector be 1. So it'll either shorten or lengthen the vector, depending on how long it already is, right? Yeah. Okay. Right. We should talk about space. Someone asked, what's the difference between normals and normalized vectors? So normals are usually a geometric term. So if you have a surface and you want a normal on that surface, that's a normalized vector that is pointing out from that surface, right? So the normals of this surface would be something like this, right? So these are normals, which also are normalized vectors, right? Or generally they are, but technically within game dev, sometimes they're not normalized, and you need to like handle that if you're doing like lighting equations and shaders and whatnot, because then the exact normals matter quite a lot. But yeah, so hi Thor. Everybody's just like, Thor. That's a cat. Hi Thor. How are you doing?
Stole my chair.
Yeah, he looks very majestic.
Also just completely black on camera.
Yeah. He's helping, sure. let's call it helping. All right, yeah. Did that make sense, by the way, the normals? So again, a normal, the term normal, when used in the context of geometry, is usually a vector pointing directly out from a given surface, right? And conversely, if you want a tangent to a surface, that's a vector that is pointing along the surface. So this would be tangent to the surface, as would this be, and so forth, right? I don't get normalized vectors. Normalized vectors, oh, sorry, heck, scene, I keep forgetting about that. Right, so these blue ones are tangents, because these are tangent to the surface. Normalized vectors could be any vectors, like any vector, like say this vector, bam, we've got a vector. What a vector. How long is this one? Let's say it's a length 8, for instance. Then this vector is not normalized. This is not normalized because the length is not 1. But if we normalize this vector, the length becomes 1, and then this would be the normalized version because this one has a length of 1, and that's about it. So yeah. Sometimes, yeah, they're also called unit vectors. Yeah, so basically, if a vector has a length of 1, it's a normalized vector. And if you have normals of a surface, they usually have the length of 1. Therefore, they are also unit vectors or normalized vectors, right? Yeah. Space. Let's talk about space. Space is super important. So this is kind of a more advanced way to look at coordinates. So we had, let's see, where did we do the first? Probably this one, where we talked about the 2D coordinates in space, right? Space is a super important concept in game dev. So if you have a, again, we're going to do yet another coordinate system because we can't get enough of those. There we go. And this is again where we probably want to mark out the actual units. Something like this. There we go. Wish I came earlier. The video is going to be on YouTube, so it's going to be there. Yeah. Okay. So let's say now we have another coordinate system. Again, works the same way as the other ones. We have 1, 2, 3. Whoops. 3, 4, 5. 1, 2, 3, 4, 5, 6. There we go. Let's do 6 here too. Actually, we might be needing these colors. Let's steal some of those. Cool. So we talked about vectors in 2D space, right? You have a point, and you can usually visualize that as a vector as well. The way you use them is kind of how you decide, is this a vector or a point, is only in how you use them and how you interpret those values. Both of them have the same value. So in this case, this has an x-coordinate of 3, right? So this is at 3, and the y-coordinate is 2, because you can track it over there, right? So now we have a point or a vector, whatever you want to call it. Oh, don't forget the origin, sure. Right, so now we have this point right here. So usually in games or in any like virtual worlds on your computer, you tend to have not only a single space for the world, but multiple subspaces of objects, or yeah, of other objects. So let's call these axes, like this coordinate system right here, this is usually referred to as world space. So I'm going to call that world space. All right, so now we have world space. So this is a coordinate, and this coordinate is at this location if we interpret that coordinate to be in world space, right? Now, things could get a bit more tricky if we have an object here. So it's still 3-2, but if you have a game object in Unity, for instance, that object in and of itself has a space. So coordinates can be relative to that object instead of being in world space. So if you have a coordinate system in that one, that is, say, you have this x-axis. No, actually, let's make that the y-axis. You have like this y-axis, and you have this x-axis in this object right here, like a Unity object, right? Wasn't long enough. There we go. Slightly better. Not good enough. God damn it. That was too long. There's no way to win. Okay, so now we have an object here. So in Unity, this would be a game object with a rotation, right? You can see that this one doesn't align with this axis and this axis because it's slightly tilted from, you know, the unit axes here. Okay, so now what you can do is that you can often find coordinates that are relative to some other thing, right? So if you, for instance, if you want to see if something is behind this object or not. Let's say the object is pointing along its y-axis, like it's looking in this direction. It's some sort of unit or whatever in an RTS or whatever. If you want to see if something is behind that one, you could use a dot product and all of that stuff, right? But you could also do something called transform from one space to another. So if you have a point, say this point right here, again, we're going to measure this in world space. So this one is at x coordinate 4, and it's at y coordinate 3, right? So we have this point right here, and then we try to ask ourselves, is this one in front of or behind the player in terms of where they're looking, right? So what we can do then is that we can use a transform function. So Unity has a lot of built-in functions called transform, inverse transform, and so forth to go between this local space and the world space outside of it. So you can use inverse transform point to go from world space, like this point right here, the world space coordinates of 3, 4. If we want to convert that to this local space right here, which has an entirely different value, where you have, the x coordinate here and the y coordinate here, in local space, this one would be something completely different. This one would have like an x coordinate of like 0.6 and a y coordinate of looks like 1 in this case. So then this is the world space position of this point, while this is the local space position of this point relative to this object right here. And these functions are, again, usually inverse transform to go from world space to some local space. If you want to do the other way around, where you want to go from the local space position to world space, this would be transform within the terminology of Unity. Right. And yeah, it's 4-3. Sorry. Heck. Yeah, it's not 3-4. What? Photoshop, stop. There we go. Alright, so transform is in that direction, and if you want to go the other direction, that would be inverse transform. So that would be going from this, All right. Okay, so I should probably clarify that this one is local and this one is world. Oh, specifically this point right here. I should probably use a different color for that one. I'm sorry for that. Writing with mouse? Yes, I am. There we go. What the heck? There we go. Sorry, I just wanted to clean this up because this is like a super important thing to learn, and then the sketch for this one was like super bad. There we go. There we go. Okay. Heck, I forgot to thank you, Polarin, when you totally subscribed to tier 2, which is insane. People never do that. Heck, thank you so much. I'm really glad that these streams have been like useful for your stuff. Thank you so much. Yeah, heck. Explaining the basics of computer graphics. I'm kind of trying to cover the essential mathematics of doing video game development. And we've covered quite a bunch of things, like value manipulation, a lot of trigonometry, vectors, angles, and all of that stuff. Yeah, so we've kind of like gone through a whole bunch of things. So now we just got to space. So now we're talking space. But yeah, so then this is kind of the fundamental way you would transform a point from one space to another one, right? Yeah. Also, Phoebe, you're using a lot of very like advanced mathematical terminology that we don't really have time or can get into. Just a heads up. but yeah, sure. Okay, did this make sense, by the way? Like that you can transform something from one space to another. I hope it does. Because these things can be relative to either world space or the space of the object. And you know, in video game development, you have so many different spaces. You have the space of the camera, you can have tangent space and shaders, you have, you know, clip space, view space, there are so many things. Yeah. Yeah, and then there are different ways to transform it as well. So for instance, if I want to transform this to world space, then if I transform, so again, all of these points are also vectors, right? So in this case, it would be a vector pointing from this one, like this, because it's a local space point. If I transform this to world space, it instead becomes this vector right here, right? Because that's how you would transform it in that way. But you can also transform them in a different sense, where instead of transforming it as a point, you can transform it as a vector. So if you have this one and you transform it to world space as a vector, which is usually referred to as, you know, instead of a point, it's just a direction information, then this one is going to transform into exactly the same angle, but it's going to be down here instead. And it's going to be in world space. So now we just did a vector transformation instead of a point transformation. Usually Unity separates it out as calling it, you know, inverse transform vector or inverse transform point, inverse transform point, and so forth. There is one more that is also called transform direction and inverse transform direction. So in Unity, a direction means that it's normalized. So if you want your vector to be normalized, doing transform direction with this one would give you a normalized vector. So it would lie within this range right here. So it would have a different length if it's transform direction, right? Yeah, so learning those three, the transform point, transform vector, transform direction, can be really, really important to make sure that you transform in the right way, right? Yeah. Okay. Right, I forgot to say that this is a local or object space. Anything you recommend reading on Laplace? Laplace's Demon? That's philosophy, not mathematics. Hey, Thor. There's some careful meows from Thor. Okay. That's probably, I think that's enough for good intro to space. Yeah, always keep track of, you know, is this vector used as a vector? Is it used as a point? Or is it used as a direction specifically? Internally, they're all stored in the same format. They're all just 2 or 3 numbers, right? Do you have interpolation on the list? I do, but I was considering skipping it. We could talk about interpolation if you want to. Oh, that one is attached to that too. It is very useful. All right, let's do interpolation. Let's do a vector here. This one is going to be called A. All right, then we have another vector. We're going to put that one at, well, we can do this one. And we're going to call this one B. All right, so let's have, let's say we want something to move from point A to point B. And we want that to like take 1 second or whatever, something easy like that, right? So if we want something to move from A to B, just in a linear path, as in a straight line from A to B, like that. If we want to make this movement, or we want to get like specific points along this this line right here, we can use something called interpolation. In this case, we're doing specifically linear interpolation, also known as Lerp. So if you want to do Lerps, and you can use that to get intermediate points between this one. So if you have the Lerp function, so Lerp, then you have the first parameter, which is the first point where you're starting off from. In this case, we want to start at A, and then we want to use the B as a target point, right? So B, you have kind of the start point and then the target point in the Lerp function. Then there's a third parameter, which is usually called T, which is just a constant. And you can give this any value. You can give it like 0, you can give it 0.5 or 1, and that will give you different points between these 2 points. So if you have the line here, if you do Lerp ABT, where T is 0, you get this point right here. So this is when T is 0. So T equals 0. Should use a slightly smaller brush. T equals 0. If T is 1, you're going to get this vector right here. So here, T equals 1. But if T is 0.5, you get a point right in the center between these two. And so forth, right? So here, T would be, So here t is 0.25 and so forth. So you can think of t as a percentage of along the way from the source to the target position, right? So a lerp between A and B, where the t value is 0.5, that vector is going to be right in the center. That's going to give you this vector right here. So that's a very useful feature. So in this case, if we wanted to animate this one across the lerp, then this would be a time value, right? If this was an animation. So then during the first second, the object would move from this location to this location, right? If we want to change the speed of that, we can do time divided by 2, and then it moves half as fast as before, or multiplied by 2 if we wanted to move that whole thing in half a second, right? Because then you would move twice as fast. Yeah, so that's how you can use Lerp. So that's you can interpolate between values like that. So if you have, you can even do that between constants. It doesn't even have to be vectors. So if you do, so Lerp is like exists in so many places. So if you do Lerp between say 2 and 4 with a t value of 0.5, then the result of that is going to be 3, because 3 is halfway between 2 and 4, right? So you can use Lerp with so many things. Like another one you can do like Lerp between the color red, and you can do and the color green, for instance. And if you do that and you pass a value of 0.5 there, then the result of that is going to be that color. Yeah, so there we go. So that's a pretty useful function. And Lerp is, again, it's ubiquitous. It's in so many places, especially if you're doing shaders. Yeah. Sorry, forgot the closing parentheses. The math of a Lerp is pretty straightforward. Not that it really matters, but because you're generally not going to write your own like a Lerp function. But if you want to do the math for that one, so Lerp between A, B, and the t value is equal to t times b plus 1 minus t times a. Heck, it's hard to distinguish these things with t and plus being very similar. There we go. Yeah. And the addition functions here work exactly the same way as it would with vectors, as with values, right? So you can just write this function and it'll just work, even if it's a vector or if it's a, a single float value, or if it's anything else, right? We need a color for t. Let's use that one. There we go. Yeah, and you can shuffle around this formula in case you want to write it in a different way. But anyway, the point of Lerps is that it's a linear interpolation between two, between 2 points, right? Can you explain the math for Lerp? I thought I did that, or do you want to explain why this works? Or so the reason this works is that this is a normalized weight where. Normalized weight? Is it a normalized weight? The weights add up to 1. So you have your point B, and then you have your point A, right? These are the two things we're working out from. And then we want B to be fully influential when t is 1, right? And we want B to not influence this at all when t is 0. So B should not be part of the equation when t is 0, and B should be the only remaining thing when t is 1, right? So what we have here is that if we do t multiplied by B, when t is 0, b is going to be multiplied by 0, and then it's going to be excluded from contributing to this value, right? And then a is the exact opposite. When t is 0, we want a to be fully influential, right? And when t is 1, we want a to cancel out. So when t is 1 here, we do 1 minus 1, which is 0, right? So then we again do 0 times a, and then this whole thing becomes 0, and then this whole thing becomes b, right? So all that's left when t is 1 is b, all that's left when t is 0 is a. And then all the values in between are a weighted sum, because the sum of t plus heck, god damn it. You know, t, did I move the whole thing? I don't know. T plus 1 minus t is equal to 1. Yeah. So basically these two have they multiply to the same weight, and that's why it's like it can stay within this range without like shooting off into weird values. Yeah. I already know that I can press X to toggle colors. I just almost never toggle between colors when I'm like toggling between these two. But I know that, but I don't know why you're mansplaining Photoshop. I like to think about this as t change from 0 to 1, and we change 0 to a and 1 to b. Gotcha. Right. Did that make sense, by the way? And again, you can use Lerp for colors too. There's another special case of Lerp called slurp, which is the best name of any function ever, because slurp sounds very silly. So say you have vectors that are supposed to be normalized across a circle or something. Then this vector is a normalized vector, and then we have another vector, let's say this one right here. And now this is going to be our b vector, and this is going to be our a vector. If you want to interpolate between these two, then doing a lerp will give you this line, but you want them to be normalized. If you do want to interpolate normalized vectors, then you don't want to have this vector right here, because this vector does not have the length of 1, right? These have the length of 1. This one is just not 1, right? So if you wanna do that, then you can use a function called slurp, which is just spherical interpolation. So instead of interpolating along a line, they're gonna interpolate along a circle like this. And they also don't have to be normalized. You can slurp vectors that are not normalized, but the point is they follow a circular arc instead of a linear line, right? Yeah, so that would be a slurp instead if you go in between these two. Yeah. Okay. Is Slurp significantly more expensive than Lerp? Probably not. Significantly, I'm not sure. It is more expensive than Lerp because you do need to have that normalization step. You either need a normalization step after the Lerp. No, actually, that's not possible. It works differently. Will Slurp get the same result of two vectors whether or not you normalize them before passing them in? I mean, if you use a slurp with non-normalized vectors, I'm pretty sure they're not going to come out normalized. They're going to still be spherically interpolated between those two vectors. I'm not sure entirely how... a slurp does not have a normalization step, but I'm not sure how slurp handles with vector A and B have different lengths. I'm not entirely sure about that. I mean, we could figure it out. I could open up Unity and try it if you want to. But I feel like we should do that by the end of this. We should do all the theory first, I feel like. Cubic interpolation? Nah, I don't want to talk about that. It's messy. It's also not as useful as Lerp. Yeah. All right. Let's see, haven't talked about rotations. Derivatives. Do we talk about derivatives? I can go through some basics. There are some like really useful things to think about when it comes to derivatives. If we talk about quaternions, I'm gonna have to do that in code, probably, because it's gonna get complicated to do like 3D rotations and use visualizing like this. Okay. Heck. I feel like I shouldn't go into how to do derivatives of equations. I should just probably... So the point that I wanted to get across is probably the relationship between... Okay, so if let's say you have an object. You have an object, it's moving, right? It's moving across something. So it's moving along some sort of path. So you can think of, you know, at 0 seconds, it's here. At 1 second, it's here. In this area. And then you have like the next second, you have it over here. So at like 2 seconds, right? Okay, so we have an object and it's obviously moving along a path right now. So one thing that I think is really, really important is to recognize that the change over position over time, right? So that would be something like meters per second, right? So meters per second is the rate of change of position, right? And rate of change is kind of a way to describe derivatives, or deltas of some value, right? So the rate of change of your position is speed, right? Because that's meters per second. I should probably save speed somewhere. Hold on. Position, there we go, equals speed. Or I guess it would be the velocity in this case. I'm so bad at planning text. God damn it. Okay. So the rate of change of the position gives you the velocity, right? And you're probably familiar with velocity now. And you can express that as a vector, and you can, like a 2D vector or a 3D vector. And yeah, delta is rate of change, exactly. So the rate of change over position, you would also say that this is over delta time as well, but that's sometimes implied. It depends on if we want to be like mathematically correct or not, but usually I feel like that's kind of unnecessary. So the rate of change of position over time would give you the velocity of an object, right? Okay, so all right. Wait, there was someone who's asking a question. Nikosma? Heck, I forgot to answer that one before. Should I use the word direction to express that my vector is vertical, or say that it's going up and not down? Yeah, 3 things, a length, direction, and a way. I'm just not sure about the words used for the last 2 to describe a vector as vertical, for example, going up and not down. I don't think there's a specific word to describe that. You would probably just say that it's going up in that case. I don't think there are any specific ones. Yeah, I don't know. Is it safe to say you moved to the US because of Twitter? It's very indirectly, yeah, sure. Okay, anyway, so the rate of change of the position, as in this position right here, would give you a because you have some sort of delta over your position, right? And if you do that over the delta of time, as in the time step that changed between these 2 points, that gives you the velocity. So it's a delta in position over delta time. But usually I like to call it like rate of change, and that's a bit more simpler, right? Okay, and then another useful concept is that if you do the rate of change over velocity, so the rate of change over velocity, what does that give us? I'm asking class this time. What do we get if we do the rate of change of velocity, again, over time? There are a lot of people who already know this, I suppose, but acceleration, exactly. This gives you acceleration. Cool, so you get acceleration. And then you get, the unit for that is meters per second squared, I think. Okay. Can we have this class accelerated a bit? Probably not. I feel like we're going at a good pace for most people in here. But a length can't be negative. Depends on if the length is signed or not. If you're talking about a speed can't be negative, because the speed is the length of the velocity vector, right? So that's probably a good thing to know as well, that speed, that P was no good. Speed equals the length of the velocity vector. So you can imagine the length function there, right? So if you want to measure the speed of some object, then you get the length of the velocity vector. Even in one-dimensional stuff, if you can have a one-dimensional velocity where an object is either moving, you know, +5 or it's moving -5, you know, the length of this one, the length of these two is the same. You know, both of these have the same speed, but the velocity is different, because the velocity is kind of space relative, whereas speed is just the length of the vector, right? Now you need to teach programming. I've already taught some programming, both in the real world as well as on stream. But yeah. All right, so yeah, this relationship is pretty important to know. So for instance, if you add to some position of each frame, like you have an update loop, and each frame you move something some amount of units, then what happens is that you just gave it a linear velocity. It has the same velocity every frame because the change per frame is the same. But if you increase that and add more every frame, you also have acceleration, right? But yeah, so knowing these two concepts is super, super useful. That the rate of change in position gives you the velocity vector. The rate of change of velocity gives you an acceleration vector. And again, acceleration can also be a vector because you can separate them out on the different axes and they can be positive and negative, right? Yeah. How would you graph that? Well, you could combine the graphs, right? We haven't really talked about graphs because I feel like we managed to get by without them. So say you have this one, you have x squared. This is now a graph of some object, and the x coordinate is time in this case, and the y coordinate is the distance it's moved, right? So the red line here is currently representing the position of the object, right? Okay, so if we do the rate of change of this one, there are some ways to convert formulas to figure out, you know, to derive a specific equation. I know the rules for that in this case. So in this case, it's just 2x. So in this case, the blue line here is the derivative of the red line. So the blue line will tell you what the rate of change is at a given point. So if you go to, for instance, 0.2, the slope of this one, or the rate of change, is currently 0.4. So this one changes 0.4 across a single time unit, right? So this blue line now represents, for any given time value, how quickly this one is increasing. And you can see that this slope is just going higher and higher, higher, which means that it's accelerating, right? It's going faster and faster and faster. This curve is like shooting up really quickly, right? Or no, not acceleration. The blue line represents the current velocity. The velocity is like slowly increasing all the time, right? If you want to get the acceleration of this one, you would derive this once more, and that would simply be y equals 2, because it has a constant acceleration. Each time, or during this whole object that's moving, it's accelerating at the same rate at all times, and which happens to be 2 meters per second squared, right? So now we've kind of gone to the bottom of this one. We can't really derive this once more. It doesn't have the next type. It's not accelerating, it's acceleration, right? The acceleration is constant, it's staying still, right? So this would be the 3 graphs for the red line, as in being the position over time, the blue line being the velocity over time, the red line being acceleration over time, right? Or not the red line, the green line being acceleration over time, sorry. Hydration is good. I hope that made sense. It can be pretty tricky to read graphs sometimes, because they don't really relate to space. They usually have like an input coordinate, which is the x value, and then an output, which is the y value, right? Okay. What else do we want to do? We haven't talked about rotations. Rotations are so messy. I feel like I should think of a... do you have examples of derivatives in your work? I mean, indirectly, you quite often use derivatives. Like, you often deal with rates of change, right? You have some object, you want to move it at a certain speed, then every single frame you need to move it by that speed, right? So actually, we can talk about framerate independence. That's a pretty important one. Let's actually make a script for that. Let's make a moving thing. Do you have examples of derivatives in your work? I can show you some derivative work. It's a shitty pun. Not even Ashley laughed right next to me. She's just like ignoring me. Whew. Gonna have to end the stream right now. Okay. Visual Studio 2019. I'm not sure. I think so. Yeah, I think I have that. Right. So let's say you have a moving thing, and you want that one to move across time or something, right? So update is Unity's update loop. This is going to run every single frame, called each frame. Okay, so now we want this one to move over time. So what's one way of doing that? Well, we can set the position of the object, which is transform.position, and then we want to move in a specific direction, let's say to the right, so vector3.right, and then we need to give this a time value. So if we just give this time.time, which is the time in seconds, this one is now going to move 1 meter per second, right? Okay, so we can go back now and recompile. How's your transition going? It's going really well. I've had a really good transition so far. I feel like I'm almost done with my transition, but yeah, it's going really well. Alright, so let's apply this to some object. Let's create a cube. Cube's a classic shape. What a solid. It's almost platonic in its shape. Let's add a moving thing to that one. And alright, so now we have attached our script to this object. And so if we just hit play now, this one is going to move along the x-axis. So press play. And there you go. Now you can see that this one is moving 1 meter per second. These grid units are in meters, right? Cool. So now that sort of works, right? So now I did this in a way where things have been, I've been using a constant or an absolute time value, right? So this one is the time in seconds. But quite often you want to do things in a more discrete way, as in, I don't necessarily know when this one is going to start, and I don't want to keep track of the start time, like when I started moving this thing, right? So in this case, I'm going to take the, wow, that's some transphobia in chat. Heck, what a jerk. Anyway, what was I going to say? Right, I was using a constant time value, but quite often you don't really know when it's going to start moving and when it's going to end that movement, right? So instead of using an absolute value, you can use a relative value. So instead of doing transform.position equals, we're going to add a displacement to that one, right? So in this case, we're going to do vector3.right, and then instead of time.time, let's say we just leave it like this. So what happens now is that every single frame, we move the current object 1 meter to the right. So if we press play on this one is going to be shooting off incredibly quickly. So if I hit play now, it just like disappears, like it's really fast, right? So now you might ask, you know, what's the speed of this one? How quickly is it actually moving? Well, the reason this can get tricky sometimes is because update is called each frame. It's not called each second. So this one is 1 meter per frame, right? And we don't want to do that. We could multiply it by 0.1, in which case it would be 0.1 meters per frame. But it would still be per frame, and we probably don't want to do that. We probably want to do this per second, right? So yeah, this is still going to work. It's still going to do 0.1, but it's still going to be related to frames. So if you play on a computer that can run the game in like 20 FPS, it's going to move slower than if you run it on a computer that can run it at 100 FPS, right? So this compensating for this issue is called framerate independence. You want your movement and your speeds and whatnot to be related to time and not frames, right? So in order to solve that, we can first like split this up into, so if we say speed, actually we don't need to do that, never mind. The way to do that is that we can simply multiply this by time.delta time. So time.delta time is the time it took for the previous frame to pass. So basically what this one does is that it changes it from being a per frame value to be a per time value. So now this one is no longer meters per frame, this one is meters per second. There we go. So now I have meters per second, and now we can probably just do, change the speed value if you want. We can make that a field if we want to. Call it speed, set it to 1, and then we're going to use speed here, right? Alright, so now we change the speed from being applied every frame to being applied on a, you know, speed per frame basis, and is now instead a meters per second value, right? Yeah. Alright, so now, if we go back here, then if we press play, this one is now moving, and now we can actually change this value while we're playing. So we can change the speed to something lower and it moves slowly, or we can change it to something fast and it moves much faster, right? We can set this to any value. We can set it to -2 and it starts moving in the other direction, and so forth. So yeah, that's kind of an important thing to do to make sure that your game is frame rate independent, right? Otherwise, you don't want to have things move faster on some people's computers and slower on other people's computers, right? Yeah, so that's usually how you make things frame rate independent. Yeah. Yeah, so basically, time.delta time helps you convert things from being a thing you should apply per second and a thing you should apply to be applied per frame instead. Yeah. Do you do this in update or fixed update? It depends on what you're doing. So in update, it's called each render frame. So each time the camera is rendering something, then update is called, right? There's another function called fixed update, as you mentioned. This is called each physics frame. So in Unity, you can set a different frame rate for your physics. So in Unity, I think it defaults to 50 FPS or 40 or something. So in fixed update, this one is actually called at a fixed rate. So you set that one in your project settings. But if you do want to make sure that you can have a consistent speed regardless of your what you set the physics frame rate to, there's another one called time.fixed delta time. This is a constant though, unless you're actually changing your yeah, in the unless you're changing the physics frame rate, but yeah. So generally, if you do this in fixed update, you want to use time.fixed delta time, which happens to also equal time.delta time when you're in the fixed update, but I usually like to be more explicit to make sure that it's using the correct delta time value, right? Yeah. All right. Yeah, I think that might be it then. Is there anything y'all feel like I missed? Something that I should talk about? Otherwise, I'm feeling pretty done, I think. Another troll. Hello. Can you report that person too? I'm pretty sure like calling for someone to kill themselves is actually against their TOS, so... Also, morally, it's a shitty thing to do. Not only against the TOS. I think it's good for one night. I think so too. I'm feeling pretty happy with this. Heck. Thank you all so much for joining. We had so many people joining in, and yeah, I really hope it was useful and interesting and such. Yeah, I really hope this might help you along the way. I'm gonna upload this to YouTube at some point, so the whole VOD is gonna be there. So yeah, if you missed some part of this, it's gonna be available pretty soon. It's gonna take a while because I have a few videos queued up. But yeah. I would also say, if you're interested in game development, if you're interested in Unity, and the stuff like that, and you want to join a community, then feel free to join our Discord. We have a Discord server. There's a link below the thing. Somebody might post it in chat as well. Steve is usually really fast at like posting the Discord link. So feel free to join our Discord if you want to join a community of other game developers, programmers, and people like that. We also, a lot of us are also under the LGBT umbrella. So feel free to join in case you want to talk about that too. We try to be a very friendly bunch of people, and we try to also ban people attacking people, and Nazis are also not allowed. So yeah, we try to keep it a nice space and environment to hang out and talk about stuff. So yeah. You can also go to my YouTube in case you want to follow the stuff that I upload there. I'm going to upload the VOD there. Yeah, I don't really pay attention to the VODs on Twitch because they have like muted music and whatnot, whereas on YouTube I remove the music track. Yeah. I think, yeah. Also, generally when I stream, I usually stream development of my own game. And the game is called Flowstorm. and that is also available on Steam. It's not public, but it's available under a closed alpha. And if you send me any donations of $10 or support me on Patreon, you can actually get a Steam key for that in case you want to play the game. So that's usually what I stream in general. So yeah, feel free to do that. It's very optional. I very much appreciate you just being here and like hanging out, being supportive, and also the subscribers and whatnot. It's super nice of you. But yeah, so if you want to go the extra mile, I do have a Patreon, and I do have, you can also donate, one-time donation if you want to support the stuff that I do. Yeah. All right. I think that's all the plugs I have. I exist on Twitter, Instagram. All those links are down below as well. Yeah. Otherwise, heck, thank you all so much for joining. I hope this was useful, and I'll see you all next time.